Chapter 7 is entropy. So entropy is actually the randomness. Okay. So the purpose of learning entropy is actually we want to track the energy lost in the process. So it's kind of an index, it's a measure to evaluate the quality of a process. Okay. So in other words, it's kind of like used to determine if a given device can operate as proposed. Okay. So remember in chapter 6, we say that for a reversible process or reversible device, reversible implies it's the best, and it's not gonna make it. Okay. So it's impossible to make a process or to make a device reversible. So as long as something is reversible, something is the best, they are best or they are reversible. Okay. But we know that in reality, no process is reversible. Okay. Reversible process is not it's not in the real world. It's not in the real world. So entropy is a randomness, so it's going to use to determine if a given device, if a given process can be, I don't know, can be good or not. Okay. And it's also used to determine if the proposed operation violates the second law. So remember the second law identifies the direction of the process. So we know that a hot coffee sitting on a desk is not getting hotter and hotter because this process, this heat addition process, this heat addition process violates the second law because this direction is not correct, it's not right. Okay. And if you want to say, later we will see this. So this heat transfer process, this heat addition to the coffee, this process violates the second law because the entropy of this heat addition process, the entropy generation of this heat addition process is actually minus, okay, which is not correct in reality. Okay, so later we will talk about this. So what is entropy? So entropy can be viewed as a measure of molecular disorder or molecular randomness. Okay, for example, like for solid, we know solid, it's solid because the molecular arrangement is regular. It's very good, it's very compact, and the molecular of a solid is not moving around, okay, not like gas. The gas molecular is moving around, right? And it's random, the moving is random, okay? So entropy is molecular disorder or molecular randomness, okay? So as a system becomes more disordered, the positions of the molecules become less predictable and the entropy increases. So entropy is randomness, it's disorder. Entropy is disorder, entropy is randomness, okay? So entropy can be viewed as a measure of disorder or disorganization in the system because it's a disorder. Entropy is disorder. Entropy generation can be viewed as a measure of disorder or disorganization generated during a process. So as like I said, entropy is a measure to evaluate the quality of a process. If the process, when we say a process is low quality, that means after this process, your system's entropy increases. Or entropy generation of the entire system, of the total system, increases. Okay, so that means this process, the quality of the process is not good. Okay. Okay. Look at this example. Molecules in the gas phase have a considerable amount of kinetic energy, or just energy if you want. However, we know that no matter how large the kinetic energies are, the gas molecules do not rotate the paddle wheel inserted into the container and produce work. Okay, so we know if this is a gas, there's a container, and a lot of it contains gas, and we know the gas molecule is moving around, so they have kinetic energy, and the mass, we know the gas has a mass, and mass contains energy. Okay, so if you insert a paddle wheel inside this container, even though we know the molecules is moving around, it has kinetic energy. However, this kinetic energy cannot move the paddle wheel to produce work. No, because of what? Let's say if we have a paddle wheel like this, and we know this molecule is moving to the left, trying to rotate this paddle wheel counterclockwise, but there are some other molecules trying to rotate this paddle wheel clockwise, maybe like, yeah, like this. This is clockwise, right? And this is counterclockwise. So these random moving molecules, they are unable to rotate the paddle wheel to produce the shaft work. Okay. This is because the gas molecules and the energy they have are disorganized. Okay. So we are unable to use this kind of disorganized energy directly. Okay. So being an organized form of energy, work is free of disorder and thus free of entropy. So like I said, entropy is disorder. Entropy is molecular disorder. But work is like nothing to do or nothing about molecules. Okay, work is not from made or by whatever the molecules. Okay, so work has nothing to do with the molecules. So work is free of disorder because it's not molecular related. Okay, and thus work is free of entropy. So this is important. Okay, work is free of disorder. And there's no entropy transfer associated with energy transfer as work. So in energy transfer, we know energy can be transferred by heat, by work, and by mass. Okay, but entropy transfer can be done by heat and mass only. These two guys, okay? Because work is free of entropy. So entropy cannot be transferred by work, okay? All right. Then any process that does not produce a net entropy is reversible. Okay, this is important, but we will talk about this later in detail. Okay, so these two guys, they are important. So this is an example why telling you why the work is free of entropy. So example like this. So if we have a shaft here and the shaft is wrapped with a cable connected to a weight. So when the shaft is rotating, then we know the weight can be like lifted up or moved down. Okay, so when the weight is moving up, then the potential energy increases, right? And this potential energy is actually the work done by this shaft. Okay, I rotate this shaft to lift this weight. So the weight's kinetic potential energy increases, and this increase in potential energy is the same as the work done onto this shaft. But when you like lower this weight, the potential energy decreases, and this decreasing in potential energy becomes the work done onto this shaft. Okay, so yeah, but the assumption is, of course, there's no friction, things like this. Okay, so the process of rising a weight by a rotating shaft does not produce any entropy. Okay, so the process can be reversed because the process can be reversed by lowering the weight. So we give the potential energy, or we transform the potential energy back to the shaft work. Okay, energy is not degraded during the process, and no potential that does work is lost. Right, so I can 100% convert, I can 100% transform the potential energy back to the shaft work, or 100% from shaft work to the potential energy, right? So this can be seen from the energy balance equation. Okay. All right, another example, I just mentioned this paddle wheel in a gas. So even though the gas temperature increases, the paddle wheel is not going to be rotated by itself or by the gas. Okay. So operating paddle wheel in a container filled with gas. We know gas has mass, and mass contains energy. So this gas contains a lot of energy. Okay. The paddle wheel is not converted to the internal energy of the gas, as evidenced by the rising temperature. So if I rotate the paddle wheel, then the temperature of the gas increases because I transform the shaft work to the internal energy of the gas. So the gas temperature increases. But when you want to do the reverse, if you want to use the gas energy to produce shaft work, you will need heat engine. You will need heat engine. And we know even for an ideal heat engine, the thermal efficiency cannot be 100%. It's always less than 100%. So that means only a portion of this energy inside the gas can be converted back to work. Okay, from chapter 6, right? Okay, so go back to entropy. What is entropy? So heat is a form of disorganized energy, and some disorganization flows with heat. Okay, so that means as long as the temperature is higher, then the entropy is higher. Okay, so if we have two bodies, they contact together, and we know in nature, the energy would go from a high temperature body to the low temperature body. So This is the heat transfer direction. Okay. So because the higher temperature body has a higher entropy, low temperature body has a lower entropy. So this entropy, this randomness, this disorganization, this disorder can be transferred along with heat, Okay. So for example, if they reach thermal equilibrium, for example, like 60 degrees, just give a random number. So after contact, after they reach thermal equilibrium, both temperature is the same, right? 60 degrees. So if the randomness of this hot body at 80 degrees is like 100, just another random number. Cold body's entropy is 10. Okay. So we know after this heat transfer process, the hot body, the temperature of this hot body decreases by 20 degrees. So the randomness would go from 100 to maybe 80, right? Because the temperature drops. So the entropy drops. Okay. But for the cold body, the temperature increases because of this guy receives some heat, right? So the randomness of this cold body, the randomness of the energy of this cold body increases from 10 maybe to 50. Okay, so I just want to show you that the randomness of the energy, which is entropy, or disorganization, or just disorder, which is the whole entropy. So scientific term is entropy. So entropy can be transferred by heat, just like this. Okay. Okay. So the second law of thermodynamics requires that the increase in entropy of a cold body be greater than the decrease in entropy of the hot body. And that's the net entropy of the combined system increases. Okay, this is actually the increase in entropy principle. Okay, we will talk about this later. Okay. All right. So the processes can occur only in the direction of increased overall entropy or molecular disorder. Okay, so processes can occur only in the direction of increased overall entropy or of increased overall molecular disorder because they are the same. Entropy is molecular disorder, is randomness. Okay. So the entire universe is getting more and more chaotic every day. It's actually getting more and more chaotic every second because we are using the energy. Every move I do, like speaking, moving my hand, things like this, I'm using computer so that my computer, my laptop consumes power. I'm using my cell phone. So all this movement increases the entropy, increases the disorder of this universe, even though it's just tiny, but still increasing. Okay. So the quantity of energy is always conserved, which is what we have been using a lot, conservation of energy. Okay. But in chapter 6, I said that the quality of energy is actually decreasing every second. As long as we use any tiny amount of energy, then we increase the entropy. We increase the chaos of the universe. Okay. All right. So Clausius inequality, this inequality, this relation serves as the base in many ideas about entropy. So let's look at this. Okay. So now we have a reversible cyclic device. This is actually a heat engine, right? This is a heat engine because there's a network output. Okay. And we know for a cyclic device, it's a heat engine. There must be some waste heat dumped to a low temperature reservoir, right? Remember, if we want to make this heat engine like 100% thermal efficiency, that means we can kill this delta Q, right? This is 0. When delta Q is 0, then our heat engine is 100%, right? So we want to save the energy, want to make the whole thing 100% efficiency. But in chapter 6, it tells us that this is not possible. It's impossible to, of course, we can minimize this delta Q, but we can never make it 0, right? Okay. Okay, so now the idea is, all right, we need to have some waste heat dumped out. So why don't we use this heat to do something? So here, there's another piston cylinder device, and this device is receiving heat from the waste heat from the heat engine. Okay, so this system can do some work onto the surroundings, right? That's nice, right? I kind of recycle my waste energy to do something. Okay, the idea is good, right? Yeah, so we do this. Okay, then we choose a new system that includes this heat engine, reversible heat engine, and include this piston cylinder device. Okay, so here is the idea. Okay, so we have a heat engine, and we know this heat engine is operating between two reservoirs, right? We have this delta Q R, the reservoir's temperature TR, and this heat engine, reversible heat engine, this guy produce network output, delta W reversible, and dump some energy to a low temperature reservoir, which is actually a piston cylinder device, okay? Okay, then, okay, so this heat engine, reversible heat engine, no problem. It follows the Kelvin Planck statement, right? It's operating between two thermal reservoir, and thermal efficiency is not 100% because we have a waste heat dumped, right? Which is a Q in this case, okay? But now let's select a new system. This is my new system, okay? And this system is, oops, this system is it's a heat engine, right? It's a cyclic heat engine, okay? Then there's a work here. Delta W system is the work output from this piston cylinder device, okay? So now I combined these two devices together to become a new system. And this system is from the energy balance. We know what? We know the combined work output is the work out from this reversible heat engine and the work out from the pistons in the device. Okay. And from the energy balance tells us this: E in minus E out. This is delta E system. Okay. So now our system is this combined system. So here I just write C to denote to let you know that this system includes the heat engine and the pistons in the device. Okay, so for this new combined system, E in here is delta QR, right? E out is delta WC, which is the summation of these two work outputs. This one is delta EC. Okay, so we can conclude delta WC, which is the summation of the reversible heat engine's work output plus the work output from the pistons in the device. This one is delta QR minus delta EC. Okay. So delta WC is delta QR minus DEC. This, yeah, if you want this delta, you can use D to replace it because here this is delta. This is delta. Okay. Okay. So this is actually from the energy balance equation to this new combined system that includes both heat engine and the pistons in the device. Okay. All right. Because this heat engine is reversible. Remember in chapter 6, when we talk about the thermal efficiency or COP, as long as your device, your heat engine, your refrigerator or heat pump are reversible, you can replace Q with T, right? So QR, I can replace this with TR, right? QR by TR, then Q by T, Q by T. So if you divide these two, it should be the same. Okay, so if you change these two guys, that becomes QR. This is delta QR over TR is delta Q over T. So we have this. Okay. Then substitute this back to delta QR. So delta QR is TR over T times delta Q, right? That becomes this guy. Then DEC is just DEC. Okay. Then I integrate this equation. And because this is a cyclic device, so this circle means it's cyclic device. Okay, it's a cycle. Okay, so the process is in a cycle. Okay, so the left-hand side becomes just WC. The right-hand side, because TR is the temperature of a thermal reservoir, it's not going to change, right? This is the definition of thermal reservoir. The temperature of a thermal reservoir does not change. So TR is a constant. So it's a constant, so it has nothing to do with the integration. So we move TR out of this integral, okay? Then this term is gone because it's a pistons in the device and the process is in a cycle. So it's in a cycle, that means U2 minus U1. U2 is the same as U1 because the final state is the same as the initial state. So U2 is U1, right? So this is delta EC. And, sorry, no. U2 is U1. So delta EC is U2 minus U1. This is 0 because the process is in a cycle, okay? Okay. Then we know that, okay, so this is a this new combined system is a cyclic device, and it has a net work output. Okay, but this new device is operating just with one thermal reservoir. Okay, so this violates the Kelvin-Planck statement, right? Because the Kelvin-Planck statement tells us that if a cyclic device has a network output, then this device has to interact with two thermal reservoirs. But this guy, this new red combined system, is interacting with only one reservoir, but it has a network output, and this device does not exist. This device violates the second law of thermodynamics. Okay, so this combined work output has to be zero, or sorry, I should say the combined work output is never be a positive quantity. So in other words, WC, this combined net work output, should be zero over a negative value. Okay, so this is the conclusion. So we got this integration delta Q over T should be less or equal than zero. TR is a positive value, right? It's a temperature of a thermal reservoir. So in absolute temperature, as long as the temperature is above 0 Kelvin, then it could be, I mean, the temperature of a reservoir should be above 0 Kelvin, right? So TR should be a positive value. So WC is TR times integral delta Q over T. This cannot be a positive quantity, so this should be smaller than or equal 0. TR is positive value, so I can just remove TR. So this is the conclusion we have. Okay, delta Q over T integral is smaller than or equal than 0. This is called Clausius inequality. Okay. Okay. So entropy is a thermodynamic property. So that means as long as we know the state, the entropy should be known. Okay. But like internal energy and enthalpy, entropy is an extensive property of a system. Okay. So the capital U, capital H, they are extensive property, right? But lowercase u, lowercase h, they are intensive properties because if you divide by the mass, that becomes a smaller one. Small u, lowercase h. Okay. So the way the difference between intensive and extensive property is that when you divide the system into half, if that property changes, then that is an extensive property. If that property doesn't change in this half-half volume, then that property is intensive, right? Okay. So entropy change of a system. So we can get the entropy change. We can get entropy from the table. We can get this from the table. So remember the steam table, the last column is entropy. We haven't used that before, but now we're going to use this a lot. Okay. So if your process if your system is internally reversible and your process is isothermal. Isothermal means temperature is a constant, right? Then your system's entropy change is delta S is 1 to 2 delta Q over T, because now your heat transfer process is isothermal. So T is a constant. So that would become 1 over T. If I use T naught to denote this is a constant temperature, then from 1 to 2 delta Q. So that becomes Q over T naught. Okay, here I don't write Q2 minus Q1. This is weird, right? Because writing this Q2, Q1, it's like Q is a property in state 1 or state 2, right? But it's not true. Q is not a property. Q is a heat transfer mechanism. So Q, this is a heat transfer. So this heat transfer makes the state 1 change to state 2. This is what Q does, right? Okay. So if your process is isothermal, then that is nice because the temperature right here has nothing to do with the integration. So we can move it out of the integral. Okay. So the entropy change of a system during an internally reversible isothermal process can be positive or negative depending on the direction of the heat transfer. Okay. If the heat transfer is to the system, then the system's entropy increases. If a system is losing heat, then the entropy of the system is decreasing. Okay. So here we conclude this. Losing heat is the only way to decrease the entropy of a system. Okay. Well, actually, losing some mass can decrease the entropy of a system. But here, the system is it's referring to an isolated system, actually. Okay. Losing heat is the only way to decrease the entropy of a system. No, I don't think the system here is an isolated system. Losing heat and losing mass, I would say losing mass is like the only two ways to decrease the entropy of the system. Okay. So let's look at this example. A piston cylinder device contains a liquid vapor mixture of water at 300 K. During a constant pressure process, 750 kJ of heat is transferred to the water. So as a result, part of the liquid in the cylinder vaporizes. Determine the entropy change of the water during this process. Okay. All right. So this is a piston cylinder device. The process is constant pressure. This heat transfer process is a constant pressure process. Okay. So if you make a temperature diagram like this, we know because the process is constant pressure, so the state falls on the curve of this one. Okay, so initial state right here, we know because the initial state is a mixture, so it's somewhere underneath these saturation lines. Okay, so I would say this is state 1. State 2 should be somewhere underneath the saturation lines here as well, because the problem says that part of the liquid in the cylinder vaporizes. That means another part of the liquid is still liquid. Okay, so this statement implies that the final state after this heat addition process is still mixture. Okay, and we know the process is constant pressure, so the temperature of the system is actually stays the same at saturation temperature at this constant pressure, even though we don't know what this pressure is. But we know from state 1 to state 2, this heat addition process, the system's temperature remains constant during this heat addition process because it's still under phase change process. Okay, so the temperature of the system is constant at 300 K. Okay, so the entropy change is 1 to 2 delta Q over T. So now we know the system's temperature is a constant. So we can move the temperature out of this integral like this. So that becomes Q over T. Okay, and Q is given, T is given, and that's it. That's all we want. Okay. Another thing I want to remind you is the temperature here, you need to use absolute temperature, apparently, right? Because you use like degree C, you would like end up with so different answers. Okay, so don't forget this is absolute temperature. You need to use K in SI unit system. Okay. Okay, so well, for this one, very first thing you need to do is to determine if the temperature of the system changes. Luckily, in this case, the temperature of the system remains constant. So if you don't have this diagram, you need to make this judgment so that you can get the entropy change as you want. Okay. All right. The increase of entropy principle. Okay, this is super important. So let's look at this. The entropy of an isolated system during a process always increases. In other words, the entropy never decreases. Okay, but saying this, there's an assumption of saying this, which is the system should be an isolated system. So isolated system means there's no energy transfer, no energy transfer mechanisms associated with this system. So Q is 0, W is 0, mass, the energy transferred by mass is 0. Okay, so the entire universe can be considered as an isolated system. So this is the reason why we said that the universe is getting more and more chaotic every day. Okay, because the entire universe, we are just one tiny part of in the universe. So the everything we do, breathing, talking, like I just mentioned, we are increasing the entropy. We are increasing the disorder in this universe in terms of the energy point of view. I say this. Okay. So the energy change of an isolated system is always greater than 0. So this equality here this equality values only when your process is reversible. Okay. All real processes, the entropy change should be greater than 0. Okay. But saying that, you need to know the assumption. The assumption is with respect to an isolated system. Okay. Okay. So for example, like if we have a piston cylinder device like this, and this device is interacting with its surroundings. We have system, we have surroundings by mass, by heat, and by work. So now we can choose a system that includes the system here and the so-called immediate surroundings surrounding these pistons in the device. And we can assume this chosen system is isolated, okay? Because for example, if like I have a hot coffee here and I choose a system surrounding this hot coffee, like in this range, okay? Then, well, even though we know this hot coffee is losing heat to the surroundings, but I assume this this effect is not gonna affect this boundary because this boundary is large enough. Okay, so this heat loss is not gonna affect the temperature outside this boundary you set. Okay, like we know the coffee, this heat loss is not gonna affect the temperature at my door, right? Because the door is far away from me, a few meters, and this energy loss is just tiny. So it's not gonna affect the temperature out there, out that far. Okay. Okay, but there's an idea you need to know. Okay, so if this coffee is losing heat, so the coffee's entropy decreases, right? Because it loses heat. However, the surroundings, the air, the ambient air, it's another system actually. So this surrounding air is receiving some heat, some energy. So the entropy change of the surrounding increases, right? Because of this heat addition process. Okay. So in this case, let's say if this is a system. So the system's entropy change is negative, but the entropy change of the surrounding is positive. Their summation is the total entropy change, okay, which is also known as entropy generation. So this total entropy change should be larger or equal to 0. Okay, so this is what the increase of entropy principle tells us. Okay, the total entropy change, the total entropy change over AKA entropy generation has to be greater than 0 or equal than 0. Then this equality happens only when the process is reversible. Okay, you need to make this, just keep this in mind, okay? So we can prove the increase of entropy principle from Clausius inequality. Okay. Right. So the Clausius inequality tells us this. Okay. So delta t, delta q over t, then integration. This is less or equal than 0. So if our process is this, So this is state 1, state 2. So process 1 to 2 is going to this dash line, but 2 back to 1 is going it's following these solid lines. Okay, so we break the integration from 1 to 2, then 2 back to 1. Okay, we just break this down. Okay. Okay, so that becomes this guy. Okay, and because this process from state 2 back to state 1, process 2 to 1, this is internally reversible. So we know that this is just S1 minus S2. Okay, it's just S1 minus S2. So if I move this term to the right hand side, that becomes this guy. Okay, right? This, they're the same. They're the same, right? And here this is S2, S1, S2, S1, right? Because I move this term to the right hand side. So this is S1 minus S2. That becomes S2 minus S1. Okay. Okay. And we can rewrite this in differential form. S2 minus S1. This is ds. Okay. Then here I just remove this integral. That becomes delta t over t, delta q over t. Okay. All right. So this guy. Okay. So this is actually still Clausius inequality. Right. I just do some manipulation, move around something. Okay. So this is still Clausius inequality. Okay. But here we know delta S is S2 minus S1. This is just entropy change of the system. Okay, straightforward. Okay. The entropy change associated with a heat transfer for a reversible, for an internally reversible process is delta Q over T, then integration. Okay. So combined with this, so S2 minus S1 is this integration plus so-called entropy generation. So actually, you can read this from Clausius inequality. So this is greater than or equal to, okay. Let me write this. If I will go from this one. Okay. So this is smaller than or equal to. Okay. But so that means if I want to remove this smaller than, I can rewrite this equation. Which is 1 to 2 delta Q over T plus entropy generation. This is S2 minus S1, right? So that means S2 minus S1 is larger than delta Q over T integration. So this S generation, which is entropy generation, has to be greater than or equal to 0. Okay, which is entropy generation, the increase of entropy principle. It tells us that entropy generation is always greater than or equal to 0, right? Okay. So, but again, this equality, this sign here, if entropy generation is 0, that means the process is reversible. Okay. All right. So for an actual process, the process in reality, because we know all the processes in reality are not reversible, which is irreversible. Okay, so for actual process, the entropy generation has to be greater than 0 in reality. Okay. Okay. So some remarks about entropy. So processes can occur in a certain direction only. A process must proceed in the direction of increasing entropy. So this is more scientific, this is more thermodynamic. Okay. We know that the process happens in certain direction, but in what direction? So it's in the direction of increasing overall entropy. I would say overall entropy, right? Remember the system. This system, if my coffee is losing heat, but then that means the entropy change of this coffee is negative, right? Because it's losing some energy. However, this energy is heat addition. It's an energy gain to the surroundings surrounding this coffee. So the air surrounding this hot coffee, the entropy change is positive. Okay, so this heat transfer process, I will write this. A coffee, hot coffee, is losing heat to the surroundings. Okay, this is the surroundings. Okay, so the entropy change of the coffee is negative. But this heat transfer process is energy addition for the surroundings. So the surroundings entropy change is larger than 0. So together, this together is delta S total over entropy generation has to be greater than 0. Okay, so every process, any energy transfer should like associate with at least 2 systems, right? For example, like this one is coffee, the other one is surrounding. So this single process involves 2 systems. So one system, the entropy of one system could like decrease, but the entropy of the other system has to increase. Then their entropy change, the summation of their entropy change has to be larger than 0. Then this process can happen. Okay. If the process is like this, if now, let's say this hot coffee is getting hotter and hotter because there's an energy transfer to this hot coffee, then, okay, so the entropy change of the coffee is greater than 0, right? Because there's a heat addition to the coffee, but the surrounding loses some energy. So the entropy change of the surrounding should be smaller than 0. So now together, the total entropy change in this case will be smaller than 0. Then that means this process is not going to happen. Okay. All right. This is the idea. Okay. So the process must proceed in the direction of increasing entropy. And this entropy means overall entropy. So every process involves at least two systems. Don't forget that. Okay. Okay. Entropy is a non-conserved property. Okay. Because entropy is conserved during the idealized reversible processes only. Okay. As long as the process is reversible, then the entropy is conserved. But for the actual processes, we know all the actual processes are irreversible. So the entropy will be always increasing. Okay. So entropy increases during all actual processes. Okay. The performance of engineering systems is degraded by the presence of irreversibilities, such as finite temperature, heat transfer, friction, phase expansion, or compression, mixing, things like this. Okay. So entropy generation is a measure of the magnitudes of the irreversibilities present during the process. Okay, so that means if the entropy generation is larger, that means the irreversibilities are more. Okay, so the greater the extent of the irreversibilities, the greater the entropy generation. Okay. All right. So let's try this. So now we have two systems and or two processes. So one process is a heat transfer from a high temperature source to a low temperature sink. Okay. Source temperature is the same in these two processes, 800 K. But the sink temperature is different. One is higher, the other one is lower. And the heat transfer is 2000 kJ. So now we are asking, the problem is asking which heat transfer process is more irreversible. So more irreversible means the entropy generation is larger. Okay, so we are looking for the entropy generation. Okay. So the entropy generation associated with a constant temperature process or isothermal process is just Q over T. Don't forget that. Okay. For isothermal heat transfer process, the entropy change or entropy generation is just Q over T. And don't forget this T, you need to use absolute temperature. Okay. Okay. So for process A, for this process, for the source is losing some energy. Okay. So the entropy change of the source for process A, the entropy change of the source is minus 2000 over 800 degrees. Okay. Okay. Don't forget the definition of a source or sink or thermal reservoir is that the temperature of a thermal reservoir never changes. Or temperature of a thermal reservoir always remains constant. Okay. So, which is isothermal heat transfer process for a reservoir. Okay. All right. But for sink, the entropy change for sink A, the entropy change is positive 2000 over 500. Okay. So together, the total entropy generation is the summation of these two entropy changes, which would be 4 minus 2.5. So this is 1.5. Okay. But for process B, the source, the entropy change for the source is still minus 2000 over 800, right? Because this heat transfer process is its energy lost from the source, right? So the entropy change of the source should be negative. Entropy decreases. Okay. For the sink, it's receiving energy, so the entropy increases. So the entropy change is a positive. So this is 2000 over 750. Okay. So together, the entropy generation, this is this much. Okay. So we could say this process is better because the entropy generation is smaller compared to process A. But here the problem is asking which one is more irreversible. Then your answer should be process A is more irreversible because the entropy generation is larger. Okay, so that is the idea. So here, I think the most important point here is that every process should like involve two systems. So one system has decreasing entropy, the other system is like increasing entropy. So together, their entropy change should be greater than 0. That ensures that the process really happens. Okay, it's very important. Okay. So entropy change of pure substances. This is about the steam table. So the usage, how to get the entropy from a steam table, the procedures, the idea, the concept, they are all the same as what you have learned previously in chapter 3, chapter 4, or even chapter 5. Okay. Because entropy is a property, so it's on a property table, on a steam table. Okay. So it's a property, that means once you know the state, you should be able to know all the properties associated with that specific state. Okay. Or you could do the reverse, right? As long as you know two independent intensive properties, then the state is known. The state is known. That means all other properties are known. Okay. So like including the quality. So you could do the quality stuff to get the entropy at the mixture state. Okay. Okay. Yeah. So using a suitable reference state, the entropies of substances are evaluated from measurable property data. So the results are tabulated. So the results can be found in a table. Okay. Okay. In the property tables, the entropy are given relative to an upstream reference state. Well, this is the idea that, okay, so even though you can get different entropies from different textbooks or from different tables, but the absolute value of these properties doesn't matter, because what matters is we want to know the change, the internal energy change, the enthalpy change, or the entropy change. Okay, so as long as you know, as long as you use the same table to get the entropy, then the entropy change is meaningful. Even though you use different textbooks, even though you use a different version of the tables, okay, then entropy change should be very close, even though the tables is different. Okay. All right. So the entropy of a fixed mass can be changed by heat transfer or irreversibilities. So this is what we just mentioned, that the entropy can be transferred by only two mechanisms, right? One is heat, the other one is mass. Okay. So if your system has a fixed mass, that means your system is a closed system, right? So in this case, the entropy can be changed only by heat. Okay. So by heat, that is heat transfer or irreversibilities. Entropy change of pure substances, just like other properties, specific volume, internal energy, enthalpy, you can get entropy from the table using the same techniques. Okay. And don't forget this. Just recall in chapter 3, I believe, if the state of the substance you are dealing with is compressed liquid, but we know that we have very limited number of the compressed liquid tables, right? So in that case, if the pressure, temperature are given, you could still use the approximation to get the entropy you want. But in this case, the table you can use is temperature table. Okay. Use the saturated liquid data in the temperature table to approximate the property you are looking for, whatever it's internal energy, enthalpy, or entropy. Okay. So similar to the energy carried by the flowing mass, right? For the flowing mass, we know the energy carried by a flowing mass is m dot plus h plus kinetic energy plus potential energy, right? Here, the entropy carried by mass is m times s. That's it. Mass times the entropy per unit mass. Okay, because S can be found from the table. Okay. All right. So let's try this example. Okay. A rigid tank contains 5 kilograms of R134A, initially at 20 degrees and 140 kilopar. This R134A is now cooled while being stirred until its pressure drops to 100 kilopar. Determine the entropy change of the refrigerator during this process. Okay. Okay. We are looking for the entropy change. So the easiest way to get the entropy change, we know if you know this is delta Q or T, then you should be able to perform the integration. But in this case, it's not easy to do that. But we know this is S2 minus S1. And we know S2 and S1 can be found in a table, in a specific table. Okay. So in this case, I would try to get the entropy from the table. Okay. Because the initial state, the pressure, temperature, both are given. So we should be able to get S1, right? We know two properties. So all others, including entropy, should be known. Okay. And this is initial state. But for the final state, we know the pressure is 100 kilopound, right? Until the pressure drops to 100 kilopound. Okay. And we need to know one more property, right? So that we can get S2. Okay. So this property should be the specific volume. This is a rigid tank. Rigid tank means the volume doesn't change and it's a closed system, so the mass doesn't change. So the mass doesn't change, the volume doesn't change, so the specific volume doesn't change. Okay, so actually you can get V1 from the given state one, the given initial temperature, the given pressure, initial pressure. So you can get V1. Okay. And V2 is the same as V1, and P2 is given, so you can get S2, you can get S1. So delta S is the mass times the S2 minus S1. This is uppercase S. Sorry. Yeah, this is uppercase S layout. Okay. But here, this is lowercase s. It's entropy per unit mass from the table. Okay. So don't forget you need to multiply by the mass, which is given. So we have the total entropy change. Okay. Okay. The other one, a piston cylinder device initially contains 3 pounds of liquid water at 20 psia, 70 degree F. The water is now heated at constant pressure by the addition of this amount of energy, of heat. Determine the entropy change of the water during this process. Okay. Okay. Okay, I got a question. Okay, let's move back here. The question is why the line is inclined in the last question. What's line? You mean this line or this line? Okay, because this is a TS diagram, and this pink solid line corresponds to a constant volume process. Okay, we didn't mention this. But actually you don't need to know this TS diagram. So you can still perform all the calculation, all the table looking stuff, right? Okay. So you don't need to worry about this, okay? Because we don't mention this kind of curve, right? Vs. V is constant. Okay. Okay. So entropy change during the mixture saturated, what do you mean? You mean state 2 is mixture? Well, I don't think that's the, you saw that one. You saw under the break curves is mixture. Yeah, of course, it's mixture. But that is the result. Okay. I mean, if you don't know this, of course, this is provided in the textbook, but in homework or in the exam, this curve, this diagram is not given. But I didn't use this diagram, right? I think the point here is you know the initial state because the temperature, initial pressure are given. Okay. And of course, when you want to find out what S1 is, then you should be able, you should know the phase first, right? In chapter 3, the procedures I listed, the very first step is you need to know what the phase is, right? So that you can use the corresponding, the correct table. Okay. So, okay, let's do this. Let's do this in real. Okay. So this is 134A. Okay, let me pull the table. Okay, let's really do this. It's R134A. So temperature 20 degrees, pressure 140. Okay. So in this case, let's try the temperature table. So pressure table. Pressure is 140 kilopascal. So I go to, because I want to know what the phase is, right? So that I can use the correct table. So go to table A12, right? This is a pressure table. So pressure is 140 kilopascal. Okay. And the saturation temperature at 140 kilopascal is minus 18. But the given temperature is 20 degrees. So it's higher than the saturation temperature at 140 kilopascal. Okay. So this information tells us that the state, this initial state, should be superheated, right? So we need to go to the superheated table, which is here, and pressure 140 kilopascal, which is 140.14 megapascal. Okay. Okay, let me see. Just curious why the temperature change in the mixture process, because usually the temperature, no, that's not correct. There's no such thing usually. The temperature and pressure stay constant in mixture. No, there's no this stuff. Okay. There's an assumption saying that, but in this case, because the specific volume is constant, it's a constant specific volume process. It's a constant specific volume process. It's not constant temperature, it's not a constant pressure. Okay, so, okay, I get this. So if you make a TS diagram, if the pressure is constant, then your curve is like this. Then during the phase change process, the temperature remains constant. Okay. If you make a PS diagram, this curve corresponds to constant temperature. Okay. We have told these two types of property diagram, but we never mentioned this kind of diagram, which is constant specific volume diagram. No. Okay. Yeah, that's the point. Okay, good. But this is a good question. Thank you. So going back to this example, okay. Pistons in the device, there's a heat addition, and we are looking for the entropy change. Okay. Okay, so initial condition or initial state, temperature is given, pressure is given. Okay, so we can get S1 easily from the table. Okay. All right. Then the final state, okay, because the process is constant pressure. Okay, so the pressure doesn't change. Okay, and apparently we need one more intensive property now so that we can get S2 from the table. But in this case, the volume changes, so the specific volume changes, temperature changes, of course, so we don't know the final temperature. Okay, but don't forget the energy balance. Energy balance tells us that E in minus E out. This is delta E system, right? And in this case, we have E in, which is Q in. We have E out, which is boundary out, right? The piston is moving up, right? So it's doing work onto the surroundings. Okay. Then the right-hand side, the energy change of the system. This is the internal energy change. Okay. And this is the clue. The process is constant pressure. So even though at this point, we don't know what the boundary work is, but we know in this case, we can combine the boundary work with the internal energy change to become enthalpy change, right? So Q in is H2 minus H1. Okay, so we can write mass times lowercase h2 minus lowercase h1. Okay, okay. So we can get h1, of course, because the temperature, pressure, they are given. So we know h1. We know the mass. Mass is here. This is the mass, right? Q in is given. Q in 3450 BTU is given. So we can get H2. Right? So we have H2. That's nice, right? So now we have pressure, we have enthalpy, so we should be able to get S2. That's all we need, right? Delta S is the mass times S2. S2 minus S1. This is what we need. Okay. Okay. Next is isentropic processes. What is isentropic? So isentropic means the entropy is the same. So entropy is the same. This is isentropic. I is entropic. Well, that just means the same entropy, the same entropy. So if the same entropy, then delta S is 0. Okay. So isentropic is a process during which the entropy remains constant. So delta S is 0. Okay. All right. This is important. a reversible adiabatic process is necessarily isentropic. However, an isentropic process is not necessarily a reversible adiabatic process. Okay. This is important, so you need to keep this in mind. Okay, reversible adiabatic together that is the condition to be isentropic. But isentropic process is not necessary to be reversible or adiabatic. Okay. So on a TS diagram, isentropic process is the process curve is perpendicular to S axis. Okay, so this is isentropic. So it's just like constant volume process, constant pressure process, right? If you have a PV, then constant pressure process, this is a constant pressure process, this is a constant volume process, right? So if now this is S, then isentropic, then your process curve is perpendicular to S. If you want, if your property diagram is like this, then isentropic process should be a horizontal curve, still perpendicular to S axis. Okay, right. In thermodynamics, an isentropic process implies a process that is internally reversible and adiabatic. Okay, so this is a hint. In this textbook, or at least in our lecture, even though we know isentropic is not necessarily, an isentropic process is not necessarily a reversible and adiabatic process, but in our lecture, we would ignore this. So isentropic is adiabatic plus reversible. Okay, or adiabatic reversible is isentropic. If your process is adiabatic, it's reversible, then this process is isentropic. And in this textbook, in our lecture, if I told you that a process is isentropic, that implies this process is adiabatic and reversible. Okay, but this is what you need to know. Isentropic in reality, isentropic process is not necessarily a reversible and adiabatic process. Okay. So engineering systems or devices such as pump, turbines, nozzles, diffusers are essentially adiabatic in layer operation. Okay. So they perform best when all the irreversibilities such as friction are minimized. Okay. So isentropic process can serve as an appropriate model for actual processes, because like for turbine or compressor, we know the very ideal one, there should be no heat loss, right? Because for example, like for a turbine, the work output is actually H in minus H out, right? Then times the flow rate. Okay. If the flow rate is given. So if there's a heat loss like this, then there should be minus a heat loss. So this is the reason why we want to insulate the pump or turbine, this kind of device, because the heat loss means some energy is lost, and the desired output is like decreasing because of something is lost, some energy is lost. Okay, so we want to make sure this device is adiabatic. we want to ensure all the energy is like being used by this device, okay? But making this device adiabatic is not ideal enough, okay? Because there might be some irreversibilities, such as friction inside the turbine, inside the pump, okay? So as long as we can minimize these irreversibilities, so your device can like perform the best, okay? So the ideal non-irreversibility process is actually reversible process, okay? So if your process is reversible and adiabatic, then your device is essentially isentropic, which is so-called the best. Okay, it's the best. Okay. So previously, when we say like when you see reversible, you can connect reversible with best. Okay, so there's an assumption for this actually, which is adiabatic if you are talking about the engineering systems or devices. Reversible plus adiabatic becomes best. Okay, and these two guys together is isentropic. So isentropic is the real best. Okay. Okay. So isentropic processes enable us to define efficiencies for processes to compare the actual performance of such devices to the performance under idealized conditions. So this so-called idealized conditions is this condition, isentropic, which is adiabatic and reversible. Isentropic process means the entropy doesn't change. Okay, so entropy doesn't change, then the entropy change is zero. Okay, so on a TS diagram, the TS diagram, so isentropic process should be a vertical line perpendicular to S-axis. Okay, so this is isentropic. So a reversible adiabatic process is necessarily isentropic. However, an isentropic process is not necessarily a reversible adiabatic process. So this is because isentropic process, there are so many reasons to make the entropy remain constant. Okay, it's not necessary to be reversible adiabatic, but if your process is reversible and adiabatic, then this process has to be isentropic. Okay, but like I said, making the entropy unchanged can be so many reasons, so many other reasons, other than reversible, other than adiabatic. Okay, so isentropic process is not necessarily a reversible adiabatic process. That's the reason. Okay, but however, in this textbook, at least in our textbook or in our lecture, an isentropic process implies a process that is reversible and adiabatic. So even though we know that adiabatic and reversible together, they are it becomes isentropic. Okay, but isentropic is not necessary to be adiabatic. And it's reversible. Okay. Need to keep this in mind. But just in this textbook, in this lecture, we would say isentropic is adiabatic plus reversible. Okay, just in this textbook. But in reality, you need to know it's not necessary to be that. Okay. So engineering systems or devices such as pumps, turbines, nozzles, diffusers are essentially adiabatic in their operation, and they perform best when the irreversibilities such as friction are minimized. Okay. All right. We need to talk about this. Okay. For example, like a turbine. If this is a turbine, so the turbine has net work out or just work out. Okay. And we know a turbine is used to extract energy from the working fluid and produce work out, right? So essentially the work out, this should be mass flow rate times H in minus H out, right? This is from the energy balance equation, right? We know from the energy balance equation, we assume a turbine is a steady flow device. So E in dot minus E out dot is 0, right? So E in here, this is mass flow rate times H in, right? And this is mass flow rate times H out minus work out, right? This is 0. So we can just do some rearrangements. Then becomes net work out is the enthalpy difference between the inlet and outlet times the mass flow rate. Okay, so imagine if you have a heat loss like this, then in your energy balance equation, there will be an additional term. So you have an additional subtraction here. So this heat loss like reduces the work output. Okay. So something like this, turbines or pumps. So for pumps, then this heat loss would be an increase of the work input, which is not what we want, right? We want to minimize the work input for the pump, and we want to maximize the work out for a turbine, right? Nozzles, diffusers, they're the same. So we don't want to have the heat transfer in these steady flow devices, okay? So essentially, these devices are designed to be adiabatic, essentially. But of course, in reality, we don't know. Usually, it's not possible to make it like completely adiabatic, but at least we try to minimize the heat transfer for these devices. Okay. So when these devices, the processes in these devices are adiabatic and reversible, then they would perform the best. Okay. So isentropic process can serve as an appropriate model for actual processes where we know all the real processes are irreversible, right? So making the process reversible is not going to be possible. So in reality, so we said that if the process is adiabatic, if the process is reversible, then your process is isentropic. But that implies that isentropic process it's not real. It doesn't exist, right? Because there's no such a thing called reversible process in reality. Okay, so isentropic process is not real. Okay, but it can serve as a limit for or appropriate model for actual process. Okay. So isentropic processes enable us to define efficiencies for processes to compare the actual performance of such devices to the performance under idealized conditions. Okay. All right. So this so-called idealized conditions is adiabatic and reversible. Okay. So isentropic process doesn't exist, just like reversible process. Okay, because isentropic process in this lecture, isentropic process means it's reversible, is adiabatic. But reversible process doesn't exist in reality, right? So isentropic process doesn't exist in reality as well. Okay. Okay, let's try this. This is a steam turbine, and steam enters an adiabatic turbine at 5 megapower for 50 degrees and leaves at a pressure of 1.4 megapower. Determine the work output of this turbine per unit mass of steam if the process is reversible. Okay, all right. So now this turbine is adiabatic and the process is reversible. So you need to remind yourself that if a process is adiabatic and reversible, then this process is isentropic, right? Adiabatic plus reversible. I think you need to memorize this. Okay, this is isentropy. That means the entropy at the inlet should be the same as the entropy at the outlet, right? This is isentropic, right? Okay. Okay, so the inlet pressure, temperature are given, outlet temperature is given, but here another property is the entropy. We know entropy at the outlet is the same as the entropy at the inlet, right? So with temperature, pressure, you should be able to get H1 and S1. Okay, then with pressure and entropy, you can get enthalpy. Okay, then the workout this should be H in minus H out. Okay, so the inlet enthalpy should be larger than the outlet entropy, right? Because that way the steam is able to extract energy from the working fluid, right? So entropy at the inlet must be higher than the entropy at the outlet. Okay, so work output is the difference of the enthalpy, okay, between inlet and outlet. Okay, all right. So the key to this problem is you need to know if the process is adiabatic and reversible, then this process has to be isentropic. Okay, So we have S2 equals S1. Okay, S1 and H1, you can get this from the table. H2, you can get this from the table, from the steam tables. Okay. All right. Property diagrams involving entropy. Okay, so by definition, we know the entropy change is delta Q over T. So this internally reversible means the system, we are looking at the entropy inside the system, and it should be internally reversible. Okay. All right, so you can just rearrange this equation T ds. This is delta Q. Then integrate both sides, then that's all, right? So Q is T ds. Okay. So Q, that tells us what? That tells us that on a TS diagram, the area underneath the process curve, this is the process curve. This area is Q. This area is Q. Okay. Okay. So isentropic process, which is mentioned, this isentropic process means entropy doesn't change, right? So entropy doesn't change, then this isentropic process curve should be a vertical line perpendicular to S-axis. Okay, and you can see this isentropic process, Q is 0, right? Because there's no area underneath this process curve. I mean, with S-axis. So Q is 0. Okay, which is adiabatic, right? Q is 0 means it's adiabatic. Okay. All right. Another diagram is Mollier diagram, okay, which is H and S. Okay. So this is particularly useful for turbines because we know for turbine or pump, okay, because we know the turbine's work output is the enthalpy difference between the inlet and outlet. Okay, so if you have a very ideal turbine, which is the isentropic process, right? Isentropic turbine, then the Mollier diagram HS, okay, should be like this, okay. Okay. And what? And you can see the area underneath this process curve, this isentropic process curve is 0. Okay. So this Q is 0. This is adiabatic process. Okay. If the process is reversible, so this is isentropic turbine. So entropy change, this is entropy change. This is H1 or H in, this is H2 or H out. So we know for a turbine, the enthalpy change is the work output. Okay. Entropy change is the is a measure of the irreversibility, right? Because if the entropy change is larger, then that means the process operated in this turbine is more irreversible. Okay. Okay. So Mollier diagram is very useful for a turbine. Okay. So it's just the enthalpy versus entropy. Okay. All right. Go back to Carnot cycle. We mentioned that we can replace Q by T if the process is reversible, right? In chapter 6, heat engine, refrigerator or heat pump, right? If the process is reversible, then we can replace Q with T. Now we are going to show you that. Okay. So remember the Carnot cycle. So a Carnot cycle consists of 4 reversible processes, right? 2 isothermal and 2 adiabatic. Okay. So 4 reversible processes. 2 isothermal, 2 adiabatic, or 2 expansion, 2 compression, right? Okay, this is a Carnot cycle. So on a TS diagram, it should be a rectangle like this. Okay. Okay. And the initial state is at this left upper corner. It should be state 1, right? So from state 1 to state 2, this is isothermal expansion, right? This is isothermal expansion. Right, because the temperature T1 is the same as T2. T1 equals T2. So this is isothermal process. Okay. And from 2 to 3, this is isentropic expansion, right? This is adiabatic. This is adiabatic expansion, but because the process is reversible, so this is adiabatic process. This is adiabatic expansion. So it should be isentropic expansion, right? So you can see that the area underneath process 2 to 3 is 0. The area underneath this curve, right? Because it's a vertical line perpendicular to x-axis. Okay. All right. From state 3 back to state 4, this is isothermal compression. Okay. State 4 back to state 1, this is adiabatic compression, which is isentropic compression. This is adiabatic, which is isentropic. This is the same. Okay, right? Because we know this is adiabatic process from 4 back to 1. It's adiabatic process, but it's also a reversible process. So together, 4 back to 1 is isentropic compression. This is a compression. Okay. So the net workout. Okay. We know I need to probably easier. TS. Okay. Okay, so from process 1 to 2, we know that the heat input is the area underneath the process curve, which is this area. This is Q in. Okay. Process 2 to 3, the area underneath this process curve is 0, right? Because 2 to 3 is isentropic process. So there's no area underneath this this process. Okay. But then 3 back to 4, this is isothermal compression. So the area underneath here, this is Q out. Okay. 4 back to 1 is isentropic, so there's no error here. Okay. So the network output is Q in minus Q out. Okay, it's Q in minus Q out, which is this area. So it's the area enclosed by these 4 processes. So this is net. Okay, network is Q in minus Q out. Okay. All right. So Q in, now we know Q in is the area, right, underneath process curve 1 to 2. So if this is S1, this is S1, which is the same as S4. Here, S2 is the same as S3. Then this is T1 equals T2. This is T3. It's the same as T4. Okay. So Q in is the area underneath process curve 1 to 2, which is a horizontal line, or let's say perpendicular to T-axis, right? So Q in, we just learned that the area is TDS, right? So Q in should be T1 times S2 minus S1, right? It's a rectangle. This is a rectangle, right? This is Q in. Similarly, Q out should be T3 times S3 minus S4. Okay. I just keep the value positive because I use the larger S minus the smaller s. Okay. All right. So the network out is T1. This is T1 S2 minus S1 minus T3 S3 minus S4. Okay. Okay. Then S2 minus S1 minus T3, then this is S3 is the same as S2, S4 is the same as S1. So this is S2 minus S1, right? So this is T1 minus T3 times S2 minus S1, which is the area of this rectangle, right? Of this rectangle. So you can see it's true, right? But this is just for Carnot cycle, okay? And what about COP? Or if we have a Carnot engine, then there's a network output, right? So we know the efficiency. We know the efficiency is network out over required input, like this, right? And network input, network out should be Q in minus Q out. Then this is the Q in. So that becomes 1 minus Q out over Q in. Okay. Then if your engine is Carnot engine, then the efficiency would become what? Would become Q out T3 S3 minus S4, then over T1 S2 minus S1. Okay. And now, because we know S3 is the same as S2, S4 is the same as S1, so they are the same. So that becomes 1 minus T3 over T1. Okay. So that tells us that if your engine is reversible, it's a reversible engine, and there's no heat loss. Of course, there's no heat loss, of course, but I mean, if your engine is reversible, then you can replace Q with T. Okay, you can replace Q with T. T1 and T3, they are because T1, remember the process of a Carnot engine. The initial state is when there's a high temperature reservoir attached to the piston, right? So T1 is actually the temperature of the high temperature reservoir, which is TH. This is actually TH. Similarly for T3, T3 is when it's a temperature of the low temperature reservoir, because at the third state in Carnot cycle, there's a low temperature reservoir attached to the piston, right? Let's look at the Carnot cycle. Carnot cycle, where is Carnot cycle? Oh, I think it's in chapter 6. Yeah. Okay, we have Carnot cycle. Carnot cycle. Yeah, here. Okay, so T1. T1 is actually TH. It's TH. Okay, and T3 is TL. TL. This is T3, right? This is T1. Okay. So this is actually TH and this is TL. So this is TL. Well, or if you want, we can keep this T1 and T3. And you know, T3 is actually TL, T1 is actually TH. Okay. So that's why we said that in chapter 6, when your engine, when your refrigerator, when your heat pump is reversible, you can replace Q by T. Okay. So we can do this from a TS diagram. Okay. Okay. All right, so this is a very good example. It tells you some important concepts about a Carnot cycle and the reason why we can replace Q with T. Okay, if in the case that your heat engine, your heat pump or refrigerators are reversible. Okay. All right. The third law of thermodynamics. Okay. A pure crystalline substance at absolute zero temperature is in perfect order, so its entropy is zero. So this is a kind of reference that if everything, including the molecules, are at absolute zero temperature, then there will be no entropy. Okay, so because entropy is randomness, is when the temperature is very, very low, then even, I mean, the Brownian motion at zero temperature is zero, right? Brownian motion is because of the thermal energy. But if the temperature is absolute zero, then there will be no thermal energy, so there's no Brownian motion. So in this case, for pure crystal substance, the entropy will be zero. Okay, this is the third law of thermodynamics. So actually we have four laws in thermodynamics. Zeroth law is when the substance A and substance B, they are in thermal equilibrium with substance C. That means substance A and substance B, they are in thermal equilibrium as well, right? This is zeroth law. First law, energy conservation. Second law is the actual process has a certain direction to happen, right? This is the second law. Third law is at zero absolute temperature, a pure crystalline, pure crystal substance has a zero entropy. Okay, so we have four laws of thermodynamics. Okay. Okay, so you need to know this. We have four laws, and you need to know every law, what every law is. Okay. Okay. Coming to some equation part in chapter 7, and we will be using these equations a lot. Okay, but yeah, memorizing all these equations is kind of difficult. So, but I think at least you need to know some important equations, so you can derive those equations you need during the time you don't have a textbook or handouts. Okay, So let's look at this. The differential form of the conservation of energy equation for a closed stationary system containing a simple compressible substance can be expressed for an internally reversible process. So this is from the energy balance equation. Okay, delta means difference. So it's just like the derivative, just like the delta here. Okay, so it implies a difference. Okay, so from the energy balance equation, we have E in minus E out. This is delta E system, right? Now we are talking about a closed system, and we assume a closed system is stationary. So there's no kinetic energy change, there's no potential energy change. Okay. So in this case, we have Q in, work in, minus Q out, and work out. This is delta U, right? System's energy change includes internal energy change, kinetic energy change, and potential energy change. But a closed system is assumed to be stationary in this textbook. So the right-hand side is just the internal energy change. Okay. So rearrange the energy balance equation with Q in minus Q out minus work out minus work in is delta U. So this is delta Q. This is delta W. Okay. The difference is the internal energy change. Okay. This is the internal energy change. Okay. All right. Then now we know from the definition, the entropy change is the heat transfer over the temperature. Okay. Delta Q is TdS. Okay. And we know this a while ago, right? The workout is PdV. So substitute this equation back to the energy balance equation, this guy back to here. Then rearrange this a little bit, that becomes TdS is du plus PdV, right? Then divide by the mass. This one is by mass. So all this lowercase stuff becomes up. Sorry, this is uppercase because lowercase, uppercase U, lowercase u, uppercase v, lowercase v. So the difference is a mass, right? Okay. So then divide by temperature, that becomes this guy, very important one. Okay. So the differential entropy change is the differential internal energy change over temperature plus P times dV over dt. So this is the specific volume differential. Okay, this lowercase v. Okay. We could do further by what? By this. We know H is U plus PV, right? By definition. So dH is du plus chain rule P dV plus V dP. Okay. So this is this equation. dH is du plus P dV plus V dP. Okay. Then so what? So we can replace du by this guy. So du is dH minus PdV minus VdP. Then there's a PdV here. So together they become just minus dH minus VdP. Okay, let's see that. We can write this one by one. Okay, delta Q minus delta workout. This is the U, right? And this term is T ds. This term is P dV. Okay, so that becomes T ds minus P dV. This is the U. Okay, then divide by the mass. That becomes T ds minus P dV. This is the U. Okay. So we divide T like this. So ds is P du over T plus P dV over T, which is this guy. Okay. Okay. Then we want to replace U. We want to replace du by dH. Okay. So we need to know what happens here. Okay. Because H is U plus PV by definition, right? Then dH is du plus PdV plus VdP. Okay. So du is dH minus PdV minus VdP. Okay. Then we put this back to here. So ds is dH minus PdV minus VdP over T plus PdV over T. Okay. So we have PdV over T, we have a PdV over T, so they can be canceled. So ds is dH over T minus VdP over T, which is this guy. Okay. The most essential, most critical equations. Okay. So all the deviations or the equations shown later will base on these two equations. So, but I'm not sure if you can memorize so many equations like this, but at least now, after showing you, you should be able to know that these equations are from the energy balance equation. Okay, then we just substitute those what we know. The Q is TdS, the W is PdV, things like this. Okay. Okay. Okay, so now we okay, so these two equations, why do we need to know these two equations? Because we want to know the entropy change, right? Because if we want to know the entropy change, then all we need to do is to integrate this equation or this equation, these two equations, either one, right? That becomes entropy change, right? This is the ds, this is ds, okay? So that's the reason why we want to know these two equations, okay? Because we want to know the entropy change, okay? So now let's talk about the entropy change for solids and liquids. Sorry, liquids and solids, okay, whatever, right? First, we need to know that in this textbook, in this lecture, liquids and solids can be approximated as incompressible substance. So what does this mean? Incompressible means the density doesn't change, right? The density doesn't change. So density and specific volume, they are like what? Upside down, right? So density doesn't change, means specific volume doesn't change. Doesn't change means remains constant, right? The incompressible substance means the specific volume remains constant. So that means dV would be 0, right? There's no volume change. There's no volume change. And we know for solids and liquids, the specific heat, I mean, constant pressure specific heat is pretty much the same as a constant volume specific heat. So we would drop out the subscript P and V. So we would just use C to represent the specific heat for liquids and solids. Okay. So so we know ds. Now we know ds is du over T plus PdV over T. Now for solids and liquids, because the specific volume remains constant, so this term is 0. Okay, so for solids, for liquids, the entropy change is just the internal energy change over T, over temperature. Okay, then we know du is C dt. Right? Don't forget this. du is Cv dt and dH is Cp dt, right? Don't forget this. But in this case, for solids, for liquids, Cp is the same as Cv, so we drop out the subscript to become C. So du is C dt. So du is C dt. Okay. Then integrate, because we want to know the entropy change. We integrate this term. So this guy becomes S2 minus S1, which is entropy change. Entropy change. Okay. Then integration C dt. So we know the specific heat might be function of temperature. Okay. Okay, but in this case, if the temperature variation is small enough, so-called small enough is actually a few hundred degrees. Okay, that is small enough, right? We know the temperature variation, we know the specific heat is function of temperature, but if the temperature variation is not so big, like a few thousand degrees. So if the temperature variation is just a few hundred degrees, then we can assume, or we could use the average specific heat to represent the specific heat. Okay. So in this case, I mean, if specific heat is assumed to be an average value, then we can move the specific heat out of the integration, out of this integral. Okay, then what remains here is 1 over T dt. then just perform the integration. 1 over t dt integration is natural log, right? So this becomes t2 over t1, okay, which is this guy. But here, this is approximate. This is just approximate. Okay. Okay. For the case that the temperature of an incompressible substance remains constant during an isentropic process. Okay, so if the process is isentropic, then this is reversible and adiabatic. Okay, so that means it's an isothermal process. Why? This is the result. This is the result. Okay, if an incompressible substance, the temperature of the incompressible substance remains constant during an isentropic process. So this process now is not, it's not only reversible, it's not only adiabatic, it's also isothermal. Okay. So T1 equals T2. Isothermal means temperature doesn't change, right? Temperature is the same. So natural log 1 is 0, right? So this is isothermal process. Okay. Oh, you could say this in the other way around, that if this is an isentropic process for incompressible substance. I mean, for incompressible substance, if the process is isentropic, then that means this process is isothermal. Okay, because for isentropic process, then that means there's no entropy change. So S2 minus S1 is 0, right? So we know for this incompressible substance, the entropy change is C average times natural log. Okay, C average, this is never 0. So we conclude that T2 has to be the same as T1, because CV, this guy is never 0. So natural log has to be 0, so that to satisfy so-called isentropic process, right? So we can know that T2 is the same as T1. So this natural log T2 over T1 is 0 to satisfy the condition of isentropic. Okay. So T2 is the same as T1. So the process is isothermal process. Okay. All right. So this is derived from the conclusion we derived in this slide. Okay. Okay. Let's look at this. Liquid methane is commonly used in cryogenetic applications. The critical temperature is 191. and thus the method must be maintained below 191 K to keep it in liquid phase. The properties of the liquid method at various temperatures and pressures are given in this table. Determine the entropy change of liquid method as it undergoes a process from 110 and 1 megaparsec to 120 and 5 megaparsec using tabulated properties and approximating liquid method as incompressible substances. Incompressible substance. There's no proof. What is the error involved in the later case? Okay. So in the later case, okay, so this is just tell us that the data you got from the tables is always correct, always the authentic. Okay. All right. So from the table, okay. So let's see if this is a liquid method. So inlet conditions, outlet conditions, they are given. So of course you can get the entropy directly from the table, right? 110 K, 1 megaparsec, 110 K, 1 megaparsec. So you have entropy right here. At the outlet, T2, 120 and 5 megaparsec. So this is the entropy. So the entropy change from the table is a difference between S2 and S1. It's 0.27. Okay. All right. Then part B, we want to approximate liquid methane as an incompressible substance because it's a liquid. Okay. So delta S is du over T, right? Is du over T. So is C average is close to C average natural log T2 over T1. Okay, so C average, we have C average right here. Okay. This is the average, then natural log T2 is 120K, T1 is 110K. So here, don't forget the unit. Let's print off. So temperature, here you need to use absolute temperature. Okay, don't forget this. All right, so this is 3.471 plus 3.486 over 2 times natural log 120 over 110. So it's about 0.303. Okay. Kj, Kg, K. So this is approximation. This is authentic. So it's about, I would say 10% error involved, right? If we approximate liquid methane as an incompressible substance. So 10% error, well, depends. I would not say it's acceptable or it's not acceptable, but there's a 10% error, okay? Next one. Okay, so this one is about money. You need to calculate the money. So I will just skip this. Okay. All right. Next is entropy change for ideal gases. Okay, ideal gases. Okay. So start from that to start from those two equations we derived earlier. These 5 stars equations, yeah, these 5 stars equations. So if you don't know, or if you want to speed up your well, your, I don't know, knowledge, your memory, or your whatever, to derive your own equations you don't memorize, then you better keep these two in mind, or you better memorize these two equations in mind. Okay, because like I said, all other equations are derived from these two, or either one of these two. Okay, so very, very important, very essential. Okay, so let's go this first. Okay, well, basically we just substitute what we have learned. Okay, for example, like du is cv dt, and pv is rt, right? pv equals rt, right? This is the ideal gas equation. Okay. So put this back to du, and put p here back to this guy. Then we have ds is cv dt over t. Then this is r dv over v. Then integrate equation, integrate, then integrate. Okay, so this integration that becomes s2 minus s1. Then we keep this term here, and r is a constant, so nothing to do inside the integral. Okay, then 1 over v dv, this is a natural log v, right? So that becomes v1, v2 over v1, natural log. Okay, so not so difficult as long as you know what those two essential equations are. Okay, another equation, another essential equation here, ds is dh over t minus v dp over t. So we know dh is cp over cp dt, then pv equals rt. So similarly, we substitute this back to here, substitute back to here, then rewrite our equation, then integrate this equation. Okay, that becomes this one. Okay. So these two, we will be using these two a lot as well. Okay. But sometimes it's confusing. It's confusing. I mean, if you want to memorize these two equations or these 3 equations, including these two are for ideal gases, right? But for solids, for liquids, this one is for solids, liquids. So you have 3 equations to memorize, or you have 5 equations to memorize if you want to derive those 3 equations by yourself. Then that's totally okay. But I think at least you need to know what these 2 essential equations are. So in case you forgot, I mean, in case if you forget the equations for liquids and solids, in case you forget the equations for the ideal gases, So you can derive those three equations by your own. Okay, so you need to know these two essential equations. You need to know what is the definition of incompressible, which is the specific volume doesn't change or the density doesn't change, right? And you need to know the du is Cv dt, dH is Cp dt for ideal gases, things like this. So you can derive those three equations for solids, for liquids, and for ideal gases, if you are able to memorize so many equations. Okay. All right. Well, we know again, the specific heat is a function of temperature for ideal gases. So we could use the average value if the temperature variation is not too big, within a few hundred degrees. Okay. So if the temperature, if this temperature is a constant, if the specific heat, these two specific heats, if they are constants, so they can move out of the integral, right? So that becomes Cv average, then natural log T2 over T1, right? The integration dt over T, this is a natural log, right? Plus R natural log V2, V1, and for this guy, this is Cp average natural log T2, T1 minus R natural log P2, P1. Okay. So yeah. I recommend you to memorize this. That's easier to use. Okay. But I'm not sure if you can memorize all these equations. Okay. Well, if you don't, then at least you need to know those two essential equations and all the property relations we have learned. Okay, so you can derive these equations whenever needed. Okay. Okay, so this is how we do this. We just use the average if the temperature variation is not too big. Okay. Okay. Okay, so if the specific heats are constant, then we can do this. It's actually the average specific heat if the temperature variation is not too big. Another way to do that is if we take the variation of the specific heat into account, then that means we should use the table. Okay. If we want to take the variation of the specific heat into account for ideal gases, then we need to use the table. Okay. So here is how we use the table for the ideal gas. Okay. So when the temperature change during the process is just too large, usually a few thousand degrees, okay, the specific heat of ideal gas vary non-linearly within the temperature range. So we have seen this diagram before, right? For those kind of inert gases, the specific heat pretty much stays constant, right? If the gas has more than 2 or even 3 atoms, molecules, then the variation of the specific heat with the temperature would be large. Okay. But here we define a function as 0. that has absolute zero as a reference temperature. So the definition of S0 is this, okay? But this is for CP only, okay? Don't forget, this is for CP only, okay? So S0 is a function of temperature alone. S0 is a function of temperature alone. This is because the specific heat of an ideal gas depends on temperature only as well. Okay, just like the internal energy and enthalpy. Okay. Then S0 is zero at absolute zero temperature. So this S0 means the initial temperature here, this is zero. So if the temperature is zero, then this whole integration would be zero. So that means S0 is zero. Okay. All right. So the very last part in the table we haven't used is, well, I'm not sure if this is the very last, but I think it's pretty much very last. Okay, it's zero, it's this column, okay, S0. So the values of S0 are calculated at various temperatures, and the results are tabulated in the appendix in our textbook as function of temperature for air. Okay, so if you have temperature, sorry, if you have the table, then go to A17. Okay, this is A17, which is the table for air. Ideal gas property for air. Okay. We use H a lot. We use internal energy a lot, the relative pressure, relative specific volume. Now, this one, we haven't used it. Okay, S0. So now you know the definition of S0 is from 0 to T, then Cp T dt over T, right? This guy, this is the definition. It's for Cp only, okay? It's for Cp. This is Cp. Okay. All right. So, sorry. Yeah, so S2 minus S1 can be rewritten, right? This is S2 0 minus S1 0, right? Right, because this S2 0 is 0 to T, I think T2, then Cp T dt is minus 0 to T1, Cp dt T minus R natural law P2 P1. Okay, then these two guys, this is actually this integral. They are the same, right? I just like divide, I just separate this integral into two integrals. Okay, and this is S2 0, this is S1 0. And S2 0, S1 0, they can be found from the table. Okay, which is I would say it's nice, right? Because we like tables. Okay, it's easier and straightforward. All we need to do is locate the value we want. Okay, so that you don't need to memorize so many equations like this. Well, sometimes you do, right? But I mean, the tabulated data is always authentic. Okay. Let's try an example here. This is an air compressor. So air is compressed from an initial state 100 kilopascal to 90K or 70 degrees C to a final state of 600 kilopascal and 57 degrees C. Determine the entropy change of air during this process by using properties from the table or the average specific heat. Okay. All right. So let's try the table. So all we need to do is to get, well, this is entropy, right? So entropy, sorry, this is air. So what we have is S0 from the table. So don't be confused. So S1 is not the same as S10. They are not the same. Okay. So S0 is not S. Okay. So 290K, 290K. We have S0, 1.66802. S2, 330K, 1.79783. Okay. All right. So the entropy change, this is S2, 0 minus S1, 0 minus R natural log P2 over P1. Okay. So we can get this easy, right? Gas constant for air, pressure 1, pressure 2, they are given. Okay. For air, I think the gas constant is 0.287, 83, right? Oh, is that true? We don't have all. I think 287. Yeah, now 3. Okay, so you have S2 0, you have S1 0. Okay. Over, this could be C P average natural log T2 over T1 minus R natural log P2 over P1. Okay. So CP average, so this is CP at 290K plus CP at 330K over 2. Okay. So you can get CP for air 290, 330. You need to do the interpolation to get the specific heat in between, or it would be easier if we can average the temperature. We can get this. Two 90 plus 330 over 2. So that would be what, 310? Okay. 310. Well, you still need to do interpolation, but that would be not too much. I think it's pretty close to, oh, sorry, this 1.005, 310, maybe 006 something. Okay. Then temperatures are given, these guys, they're the same as a part A. So you can compare. Okay. So let's try. We can try S2 minus S1. So the difference is 0.12981. Okay. Pressure P2 600, P1 100. So natural log 6 times 0.287. This is minus. Oops. Yeah. Okay. How about this? So let's say the CP at 310. Oh, let's just do 6. Okay. Yeah, I would say just 6. Okay. So 1.006 times natural log T2 over T1. T1 is 290 minus natural log 6. Okay. So the difference is, I think, pretty small. It's pretty small, so it's acceptable. Okay. All right. So delta S is negative in this case. Let me see. All right. Yeah. 3, 8, 4, 24 is 24. Yeah. So entropy change in this case is negative. It's okay, right? Because we know a system's entropy change could be positive, could be negative, but the entropy generation should be positive. But this is not about the entropy generation, right? Because we didn't do the calculations for the entropy change for I would say the environment. This air compressed does. Okay, because the process in this compressor could like affect the environment. For example, like there's a work output. Well, work output, it's work, so it's nothing but other process or some kind of irreversibilities inside the compressor. Together, their mixing effect could affect the environment. So if you want to get the entropy generation of this process, we need to do something more, which will be introduced later. Okay. All right. Constant specific heat for isentropic process for ideal gases. Okay. So we know this. We know this, right? This is the one. This is another one. Okay. for isentropic, so isentropic means entropy change is 0. Okay. Okay. So in this case, what do we have? What do we have? If this is 0 for isentropic process, then nature log, we have nature log here. Okay, let's do this. For ideal gas, entropy change is CV nature log T2, T1, I think plus or nature log P2, P1, right? Yeah. So if this is if the process is isentropic, this is 0, right? So we can move CV and R inside the nature log, right? So that becomes nature log T2, T1, CV plus nature log P2, P1, R. This is 0. So T2 over T1, CV is minus P2 over P1. Okay. Okay. Then, well, oh, it's V. It's V, not P, right? See, so I made a mistake in the class. So you might make the same mistake in the exam. V2, V1, this is V2, this is V1, this is V, this is V, okay. All right, you need to know this, okay? In chapter 4, I believe, for ideal gas, CP is CV plus R, or the specific heat ratio, which is CP over CV, okay? So CP is CV plus R. Specific ratio is CP over CV. Okay. So together, I want to replace the purpose here is I want to eliminate R. Okay. So R is CP minus CV. Okay. And CP is KCV. So R is CP is KCV. So R is CV K minus 1. Okay. So we put this back here. So T2 over T1 CV, this is minus V2 V1. This is R is CV K minus 1. Okay. Okay, then K minus 1, then what do we do? Then I put this minus. Hold on. I have a minus. Well, okay. Yeah, so if this is nature log, this is nature log. So this minus can actually goes into the exponent here, right? Yeah. Yeah. So this minus should go to here. Right. Let's start over this little bit. Okay. Let me finish this. So nature log T2, T1, CV, this is minus nature log V2, V1, okay. And this minus can go to exponent here, go to nature log here. So that is nature log T2, T1, CV. This is nature log V1, V2 minus R. So if I put minus here, back here, so that becomes V1 over V2. Okay. So T2 over T1, CV is V1 over V2 plus R. Okay. Then R, put this back here. So T2, T1, CV, this is V1, V2, R is CV, K minus 1. Okay, so CV, CV here can be cancelled. So this is the remaining. T2 over T1, T2 over T1 is V1 over V2 to K minus 1, to K minus 1. Okay, but don't forget, this is when the process is isentropic. So I made a mark here. So this is under the condition when the process is isentropic, which is constant S, means isentropic. Okay. So from the first isentropic relation for ideal gases under constant specific heat assumption, we know this. But for isentropic, so isentropic means the entropy doesn't change. So the entropy change is 0. So we can end up with this relation. Okay, we you just assume this is negative R, right? Well, let me write this. Okay, so entropy change. Sorry. S2 minus S1. Entropy change, this is CV nature log T2 over T1 plus R nature log V2 over V1, right? For isentropic, no, this is for ideal gases. With constant specific heat, okay? So if the process is isentropic, that means S2 minus S1 is 0, right? Because S2 equals S1. So in that case, CV nature log T2 over T1 plus R nature log V2 over V1. This is 0, right? So that means CV nature log T2 over T1 is minus R nature log V2 over V1. Okay, so now we move CV back into the nature log. So that would be T2, T1 to CV power. Okay, this one is nature log V2, V1 minus R. Okay, so we have T2, T1, CV is V2 over V1 minus R. Okay, but we know for ideal gas, Cp is Cv plus R, and K is Cp over Cv. Okay, so we know that R is Cp minus Cv, and Cp is Kcv. Okay, so this can be Cv1 K minus 1. Okay, this is a K minus 1. This is R. So put this back to here, then we would have T2 over T1 to Cv. This is V2 over V1. This is a minus R, so that would be Cv1 minus K. This is a K minus 1, but we have a minus here. Okay, so we can kill Cv here. So that becomes T2 over T1 is V2 over V1 to 1 minus K. Okay, so we have this T2 over T1 is V1 over V2 K minus 1 over 1 minus K, which is the same, right? It's V1, V2, then K minus 1. This is the same. Okay. All right. So similarly, for the second isentropic relation, which is S2 minus S1, this is Cp natural log T2 T1 minus R natural log P2 over P1. Okay, so if the process is isentropic, then this is going to be 0. Okay, so we would have Cp natural log T2 T1. This is R natural log P2 P1. Okay, again, move this back to the natural log, then we would have T2 over T1. Cp is P2 P1 R. Then this is P2 P1. R is this, and we could write in Cp. So that could be Cp minus, so Cv is Cp over K. Okay, so this is Cp 1 minus 1 over K. Okay, so we have T2 over T1 is P2 P1 to K minus 1. Okay, which is this guy. Okay. All right, so first isentropic relation, second isentropic relation, then, well, then you can see this is T1, T2 over T1, this is T2 over T1. So these two guys, they should be the same. They should be the same. Okay, which is this. Okay. Yeah. Okay. So together, we have these three very, very useful and important equations to use. If the process is isentropic, if the working fluid is ideal gas, if the specific heats are assumed to be constant. Okay, so you need to satisfy these three conditions. So we have these three equations to use. This is for ideal gas, of course. and when the process is isentropic. And when the specific heat is constant. Okay. Three conditions, as long as these three conditions are satisfied, then you have these three very useful equations to use. Okay. Okay, so you can see this is a constant specific heat, isentropic process, isentropic processes, and ideal gases. Three conditions, three equations, very useful. Okay. All right. Okay. So, in what kind of conditions that we can consider specific heats constant? Okay. So remember in chapter 3 or chapter 4, maybe, when we talk about the specific heat of ideal gases, we know that specific heat vary with temperature. Okay. However, as long as the temperature variation is small enough, it's usually within a few hundred degrees, then we could use the average specific heat to represent the real specific heat, right? So I mean, if the temperature variation is small enough, then we can see that the specific heat vary with temperature almost linearly. Okay, so as long as we need like something, I mean, as long as we need something specific heat times delta T, then we can use the average specific heat to do that, right? It's like Cp delta T, but we use Cp average, things like this, right? Okay, so what about if we need to consider the variation of the specific heat? Okay, so this is the real case. The specific heats vary with temperature. Okay, so if you're working for its ideal gases, and these ideal gases are like undergoing isentropic processes, and we need to take the variation of the specific heat into account, then how do we do? Well, as long as you see this variable specific heat, or saying like taking the variation of the specific heat into account, things like this, that implies that the problem is asking you to use tables. Use tables, okay? And we know this. We know in the table for ideal gas, for example, like for air, we have S0, right? And this is defined as Cp dt, right? It's Cp dt. Just like this, yeah. Cp dt over T, yeah, I missed one, over T. Over T, okay. So this one is valid only for the second relation of isentropic relation, right? Because the second one, this one, this term is Cp, and S0 is defined by Cp, not Cv, okay? So yeah, that's it. So if your process is isentropic, that means this guy will be 0, right? Isentropic means entropy doesn't change, so it's 0. So you can have this, and you can use table to get S0. And S0 is function of temperature because Cp is function of temperature. This is just temperature. So S0 is function of temperature for ideal gases. Okay. All right. Then in the table, we haven't used other two properties. If you have table, you can just go to A17. Okay, so A17 is ideal gas properties of air. Okay, so we know now we have enthalpy, we have internal energy, and we have S0. And we have been using H and U a lot. And we know for ideal gas, enthalpy, internal energy, and S0, they are function of temperature only. Okay, now let's talk about PR and VR. Okay, so PR and VR, they are relative pressure. This is PR. Relative specific volume. This is VR. Okay, so it's different when we talk about PR. In chapter 3, when we were using the compressibility chart, remember we have PR before, but this is a capital R. Okay, this R is lowercase r. So this R means reduced. Okay, so don't be confused about lowercase r and uppercase R for the pressure. Similarly, for specific volume, we have reduced specific volume in chapter 3 before. And R here, we use uppercase R. Okay. All right. So now, again, for ideal gas, this is for ideal gas, isentropic process. Okay, so we have this. Okay. Then we just do some rearrangement like this. Let me write this. S2 for ideal gas, isentropic process. So S2, 0 minus S1, 0, then minus R, natural log, P2 over P1. This is 0, right? Minus R, natural log, P2 over P1, this is 0. So that means S2, 0, minus S1, 0. This is R, natural log, P2 over P1, right? And we move R back into this natural log, becomes this, right? And we expand, we want to remove natural log. So when we remove natural log, then we would end up with this P2 over P1 to R. This is exponential S2. Oh, sorry, no. Wrong. This is R. Then what I'm gonna do is supposed to remove R to the left-hand side like this. Then we remove the natural log. So P2 over P1 is exponential S2 0 minus S1 0 over R. Okay. Then we can split this term. So that becomes exponential S2 0 over R minus S1 0 over R. Okay. All right. This is the exponent to exponential. So we can split it up by this. This is exponential to R S2 0 over exponential to S1 0 over R. Okay, so we define this exponential S2 0 over R. This is PR2, and this is PR1. So the definition of PR is exponential S0 over R. Okay. So we have this important conclusion. The pressure ratio for ideal gas undergoing an isentropic process is the same as the relative pressure. It's the same as the relative pressure ratio. Yeah. So this is a pressure ratio. This is a relative pressure ratio. Okay. All right. Then similarly, we could do this from PV equals RT. So P2 V2 over T2, this is P1 V1 over T1. This is just from the ideal gas relation, right? PV equals RT. So PV over T is R, and R is a gas constant, so it's not going to change. So P2 V2 over T2 is the same as P1 V1 over T1. All right. Then let me see. I want to know V1 over V2. So V1 over V2 over V1. V2 over V1 is V2 over V1. This is a P1, P2, then T2, T1. Okay. Okay. So if your process is isentropic, if the process is isentropic, then we know P1 over P2, this is P1R over P2R, right? Then T2, let me see. Yeah, T2, T1, like this. Then we group these two guys together, we group these two guys together, then that becomes T2 over P2R over T1 over P1R. Okay. Okay. Then this is V2R, and this is, I think I should write VR1, and this is VR2. Okay. So we define the relative specific volume as temperature over PR. Okay, I should write PR2, PR1. Okay, PR1, PR2. Okay. Okay. So we have these two important conclusions that for ideal gases, isentropic processes, variable specific heat then P1 over P2 is PR1 over PR2. Okay. V1 over V2 is VR1 over VR2. Okay. And okay, so we know that PR is function of temperature for ideal gas, right? Because S0 is function of temperature. R is a constant. Okay, so PR is function of temperature. And VR, this is also a function of temperature only, right? Because PR is function of temperature, and this is temperature. So VR is also a function of temperature. So PR and VR for ideal gas are functions of temperature only. Okay. Okay. So you can see this. PR and VR, they are function of temperatures only. Just like S0, just like enthalpy, just like internal energy. So all these 5 properties for ideal gas, for air, they are function of temperature only. Okay. Okay. So now we have 2 situations for ideal gas. Isentropic processes. One, when the specific heat are constant. You have 3 very useful equations. One is PV to K, this is a constant. And TV, I think it is K minus 1, it's constant. Another one is, I don't know, TP K, 1 minus K. Let's see, let me check. PVK, TV K minus 1, TV K minus 1, then TPK 1 minus K, yeah. Okay, this is when the specific heats are constant. Okay, this is one situation. The other one is variable specific heat. Then we would have like P2 over P1 should be PR2 over PR1. And V2 over V1 is VR2 over VR1. Okay, then that implies you need to use tables. Okay, so just for ideal gas, just for isentropic process, 2 situations: constant specific heat or variable specific heat. Okay, then you have like these 2 options to do your homework or problem. Okay. All right, so look at this example. It's saying that air is compressed in a car engine from 22 degrees to 95 and 95 kilopascal in a reversible adiabatic manner. So don't forget a very important idea. When the process is reversible and it's adiabatic, so together, this is isentropic, right? Reversible plus adiabatic, that becomes isentropic. So it's ideal gas undergoing an isentropic compression. Okay. if the compression ratio V1 over V2, so this is the volume ratio. Okay. This is a piston cylinder device, so it's a closed system. So the volume ratio is the same as the specific volume ratio, right? So the specific volume ratio is also 8. Okay. We are looking for the final temperature of the air. Okay. So this example is just telling you that we are interested to know the final temperature, but it doesn't tell you that if we need to take the variation of the specific heat into account. So we could do both. Okay. So first, let's assume the specific heats are constant. Okay, we do that. So ideal gas, isentropic process, constant specific heat. So we have TV to K minus 1 is constant. So T1, V1 to K minus 1 should be the same as T2, V2 to K minus 1. Okay. So T1, we know T1 is given, and well, yeah, T1 is given. We are looking for T2, but the specific volume ratio is none. So T2 is T1 times V1 over V2 to K minus 1. T1 is given. The volume ratio or the specific volume ratio is given. So as long as we know K, we should be able to determine T2 through this relation, right? But now question is, we don't know K. We don't know K. But if you go to the table, you will see that for air, K is a function of temperature as well. Okay, so that's why we say that if you want to use this relation, you need to know, you need to assume the specific heat is a constant. Okay, so in this case, well, we don't know T2, so we are unable to determine K. That's the point. Okay, that is a big point. But in this case, we could guess, because you can see the initial temperature 295 K is around 300 K, whatever, is 1.400. And you can see within a few hundred degrees, like all the way to 650, the change is just 0.03. 0.03 is like 20%, right? 0.03, yeah, right? Let me try. 0.03 over 1.4, yeah, 20%, around 20%. Okay, so it's not just too much. So if you could use the specific heat somewhere between 300 and 650, that would be reasonable. Okay, for example, well, in the textbook, it uses this K, 1.391. Okay, so if K is K at 450 K, then the temperature you could get T2 is 662.7 K. Okay. Okay, but well, if this situation, if this problem gives it's given in the exam, we will let you know what K or at least what specific heat you need to use, or we will give you the full condition. Okay. All right. This is one. We assume the specific heats are constant. Okay. In another case, now we assume we need to take the variation of the specific heats into account. Then that means you need to use the table. You need to use the table. Okay. So here is the idea. Okay. So we know the specific volume ratio, and we know this is ideal gas, this is isentropic process. So the specific volume ratio should be the same as the relative specific volume ratio. So V1 over V2 should be the same as VR1 over VR2. Okay. So you can get, because VR, the relative specific volume, is function of temperature only. So you can get VR because T1 is given. Okay. So VR 295, need to use A17. 295, VR is this. And this is VR2. And we know the ratio is 8. So you can get VR2, which is almost 81. And you have 81 VR, then you should be able to get the temperature. 81 should be somewhere between these two, right? So you need to do the interpolation to get the temperature. So it looks like the temperature should be a little bit higher than 660. Okay. So T2 is 665. Okay. All right, so you can see it's not too far away if we assume the specific heat is constant or not. Okay. So, and you can see that T1 is almost 300 degree K, T2 is 665 degree K, so it's around 350 degrees difference. So not too big. So we can use the average specific heat in this case, and that would result in reasonable results, right? Okay. So depending on the problems, usually depending on the problem would tell you that, okay, we could assume the specific heats are constant, or we need to take the variation of the specific heat into account. Okay, it's two situations. And you need to know that in general, as long as the temperature variation is in a few hundred degrees, then assuming a constant specific heat is reasonable. It's reasonable enough. Okay, this one is authentic, right? Everything from the table, everything that comes from the table is authentic, is accurate. Okay, so not too much. All right. Another example, helium gas is compressed by an adiabatic compressor from an initial state, 14 psia, 50 degree F, to a final temperature of 20 degree F in a reversible manner. Reversible adiabatic, so you know this compression process is isentropic. We are looking for the exit pressure of helium. Okay. All right. Again, you could do both. assume the specific heats are constant or assume a variable specific heat. Okay. All right. So let's try constant specific heat. That's easier, right? Because if the process is isentropic, if the specific heats are constant, then we have three very useful, very beautiful equations to use. Okay. So that would be TP 1 minus K over K. This is TP. Yeah. TP to 1 minus K over K. This is constant. So T1, P1, 1 minus K over K. This is T2, P2, 1 minus K over K. Okay. So we know three stuff. T1, P1, we know that. T2 is given. And so as long as we know K, then we should be able to get P2, right? As long as we know K. So, but in this case, it's good because of what? Because of the initial temperature and the final temperature, they are both given. So we could just use the K at the average temperature. So that means we could use K at average, what's the average temperature here? 375 over 2, 187.5 K. Okay, so you just go to the table, see if you can get the specific heat ratio of helium. No, we don't have this. I need a full table. Helium. No. Okay. We have helium. But this is not what we want. Okay, so we have helium. Okay. So helium K at 300 K is almost a constant. So let me check, double check. No, so this is what we got. We got K 1.667 at room temperature. Okay. Well, not close to room temperature, but this is all we have. Okay. So we could just use K 1.667 then to get P2. Okay. This is one way to go, of course. Okay. The other way to go is to use the table. We assume what? Variable specific heat, right? So P2 over P1. This is PR2 over PR1. Okay. So we can get PR2 and PR1 because T2 and T1, they are both given. Okay, because relative pressure is function of temperature only. So as long as we know the temperature, we should be able to know the relative pressure. So we can get a real number here. P1 is given, so we can get P2. Okay. So using this, using constant specific heat and K is 1.667, the pressure here is 14.5 psi. Okay. Okay. So if you have table for helium, then you could do this, of course. Then you can compare if this P2 and this P2 is the same, is similar, or far away from each other. Okay. Okay. Next, we are going to introduce a very useful and important idea, okay, which is reversible steady flow work. Okay. Just recall that for closed system, the boundary work is PdV. Okay, it's PdV. Well, this is nothing about what we are going to talk about, but just remind you, we have this because the reversible steady flow work is VdP. Okay, so it's just like not upside down, but I mean switch the parameter, right? For closed system, the boundary work is PdV, but for steady flow system, which is an open system, the reversible flow work is VdP. So it's a little bit different. So we can derive this starting from the energy balance equation. Okay. We know for a steady flow device, whatever is pump, is compressor, or what, steady flow device, the energy balance equation is the heat input minus work output. This is the enthalpy change plus kinetic energy change plus potential energy change. Okay. So now delta Q, we know this is TdS, right? And TdS is dH minus VdP. Okay. So delta Q, that tells us delta Q is dH minus VdP. Okay. And we put this back to the energy balance equation. So dH minus VdP minus delta work. This is dH plus dKe plus dPe. So we have dH on both sides. So we can cancel these two out. So we have minus delta W. This is VdP plus dKe plus dPe. Okay. Then we integrate this equation. We have reversible steady flow work. This is a minus VdP minus delta Ke minus delta Pe. Okay. This is what we have here. Okay. We just integrate, then we got this. We got this. Okay. Or specifically, we remove the minus sign and specify the direction. This is the work in. Okay. So that's why for steady flow system, the reversible steady flow work is VDP. It's just opposite, it's just different, little bit different from the boundary work of a closed system, which is PdV. Okay. So if the working fluid is incompressible, by definition, incompressible means the density doesn't change. Constant density. Okay. If well, density and the specific heat, they are upside down, right? So incompressible substance or incompressible fluid means the specific volume is also a constant. Okay. So the specific volume is a constant, then this guy has nothing to do with the integration, right? So we can move this out of the integral. Okay, so we end up with this. The reversible steady flow work is minus V, which is a constant in this case, delta P, right? Because this V has been moved out of this integral. So that becomes just delta P, then delta KE, delta PE, this is delta KE, delta PE. Okay. All right. So for steady flow of a liquid through a device that involves no work interaction like nozzle or pipe, then the work done, this work should be zero. Should be zero for nozzle, for pipe, or diffuser, of course. Okay, right? Because these devices, they don't consume work, they don't produce work either. Okay, so the work should be zero. And this is famous Bernoulli equation. Okay, this is a famous Bernoulli equation. Okay, so you will learn this in fluid mechanics, maybe next year. Okay, all right. And another thing is like, I like this diagram. It's interesting because literally you can see these three equations, they are the same, right? Except the font size, okay? The font size is different. So when the font size is larger, that means the work is larger, okay? So you can see this is small v, so we have small w, medium v, medium w, large v, and large w, okay? So it's just interesting. So it just tells us that the larger the specific volume, the greater the work produced or consumed by a steady flow device, okay? So the reason to mention this is because later when we will talk about the compressor work consumption, right? We know a compressor or a pump, they consume work, right? So we want to the work consumption, which is actually energy consumption, minimized. Okay, we want to minimize the work consumption for a compressor or work. So the way to do that is actually just to make sure you have small specific volume. Okay. The way to ensure you have small specific volume is you keep the working fluid cool. I mean, literally it's cool. Okay. So we know the specific volume varies with temperature, right? When the temperature is higher, then the specific volume is larger. So if you want to minimize the work input to a pump or to a compressor, you need to make the specific volume small. If you want to make the specific volume small, you need to make your working fluid cool. as cool as possible. Okay, we will talk about this later. Okay. Yeah, just right here. So okay, so this we want to determine the compressor work input required to compress steam isentropically from 100 kilopar to 1 megapar, assuming the inlet inlet state is saturated liquid and saturated vapor. Okay, so these two situations, well, usually we know pump and compressor, they are essentially the same stuff, right? They consume power, they transfer the power input to the working fluid, right? But actually pump usually refers to compressing a liquid. Compressor is usually, well, yeah, compressor usually refers to compressing a vapor or compressing air. Okay, so this is air compressor, and this is liquid pump. Okay, so that is the, I'll not say tiny difference, but at least it's a difference between pump and compressor. So pump is used to compress liquid. Compressor is used to compress air or gas. Okay. All right. So we are looking for, oh, sorry. We are looking for the work input for these two cases. Okay. So, well, so now we know this compressor or this pump, they do compression isentropically. Okay. So if you have table, then the work input is H out, or H2 in this case, H2 minus H1, right? Based on the energy balance equation, right? We know work input for a compressor or for a pump is the enthalpy difference between its inlet and outlet. So this is the work input. So as long as we can find out what the enthalpy is, then we should be able to get the work input directly. Okay. So, and in this case, well, you can see, so we have two properties, or at least we have these two information. We should be able to get H1 and S1, right? And we know the compression process is isentropic. So S2 here is the same as S1. So with these two information, we are supposed to be able to get H1 from the table directly. Okay. Similarly, it's the same for case B. We know it's 100 kilopar saturated vapor, so we can get H1, we can get S1, and we know S2 is the same as S1, so we can get H2. This should be H2. Okay. Okay, so theoretically, if you have tables, you could do this easily. Okay. However, well, I would say for this guy, for case B, yes, you can get H2, you can get H1 from the table. But here, the problem is for case A. For case A, let's try if we can get this from the table. Okay. So for case A, at inlet, we know P1 is 100 kilopar, and this is saturated liquid. So we can get H1 and S1. Okay, so go to the table, and 100 kilopar, we need to A5. So 100 kilopar is right here. It's saturated liquid. So entropy is this 1.3028. And enthalpy is 417. Okay. All right. Then P2 is 1 megapart, which is 1000 kilopart. And S2 is the same as S1, it's 1.3028. So with these two information, 1000 kilopart, which is here. Okay. 1000 kilopart. Okay, yeah. So you can see at 1000 kilopart, the saturated liquid point, the entropy is larger than the given entropy, right? This is 2.1 something, but your entropy is 1.3. So that tells us that at the outlet of this pump is compressed liquid. It should be compressed liquid. Okay. But let's try. We have compressed liquid table, right? We have compressed liquid table here. Yeah, this is a compressed liquid table. But you can see the minimum temperature provided in the compressed liquid table is 5 megapart. So we don't have table to do that. We don't have table to get H1, right? If the temperature, if T2 is given, then at least you could do the approximation, right? You could do H1, H2 should be HF at T2 approximation, right? This is what we have learned, but we don't know T2. So you are unable to do this, but this gives you a big hint. I'm not sure you have been aware of this, okay? All right. So we know at inlet of the pump is saturated liquid. Saturated liquid is liquid. At the outlet, it's compressed liquid. So that means the entire pump, the working fluid, the water in this pump is all compressed liquid. Okay, it's all compressed liquid through the entire compression process. And we always assume the compressed liquid is incompressible. So incompressible means the specific volume is a constant, right? So that means you can get specific volume from the given inlet condition. You can get this. And this is constant. Okay. So the reversible steady flow work in this case is just V dP. And this V is a constant. So this is actually V1. Okay. Then dP integration is just P2 minus P1. P2, P1, they are given. V1 is right here. So V1 is here, 0.001043. Okay. So you have the reversible steady flow work. Okay. All right. So, and for case B, like I said, for case B, you can really get the enthalpy from the table. Then the work input is just the difference between these two enthalpies. Okay. So let me give you the answers. For part A, for case A, For case A, the work required is just 0.94 kJ/kg. And for case B, this enthalpy difference is almost 520. Okay. So you can see that compressing liquid requires much more energy than compressing an air. Okay, it's very, very different. Okay. Next, so like we just mentioned, the reversible steady flow work is VdP. So if you want to minimize the work input for a compressor, you would need to minimize V as possible as you can. Okay, so minimizing the specific volume for ideal gas, the way to do it is just to keep it cool. Okay, cooling the gas. So you can make V small. Okay. Okay, so we have like 3 different ways to cool the gas. One involves no cooling, one involves little bit cooling, and the other one is maximum cooling. Okay, 3 kind of process to cool the gas. So what is the process that involves no cooling, which is isentropic, right? Because we know isentropic means it's reversible and adiabatic. Well, if your device is adiabatic, how do you do cooling, right? Cooling means there's a heat transfer, right? But your device is adiabatic, so it involves no cooling. Okay. If your process is polytropic process, well, there's some cooling. Okay. For isothermal, involves maximum cooling. So I want to start from a PV diagram. So just recall, for a closed system, we know the boundary work is PdV, right? So in a property diagram, PV, like this, if this is the process curve, then PdV means the area underneath this process curve. So the area with the curve and V-axis, this is the boundary work, right? But now for steady flow devices, the reversible steady flow work is VdP. So on a PV diagram, then this VdP is the area between the curve and P-axis. This is P, this is V. This is reversible steady flow work. So it's different, right? This is P dV, and so the curve and the V-axis, the area in between is the boundary work. But in this case, this is dP. So the area between the curve and P-axis, this area is steady flow work. Okay. Okay. So if you look at this diagram, okay, the isentropic process means there's no cooling. Isothermal process is maximum cooling. So you can see the maximum cooling means the steady flow work is minimum. Okay, so you can see this area is smaller than this area, right? The yellow area is the isentropic cooling, which is no cooling actually. The blue area is isothermal cooling. Okay, so you can see this yellow steady flow work is larger than this blue steady flow work from the comparison between these two areas. Okay. All right. Then now we want to know what this steady flow work really is. Okay. So how do we know this? How do these equations come from? Well, you just perform the integration. Just put this PV equals constant because you want to minimize the work, so your process has to be reversible. Okay. And isentropic process is adiabatic, is reversible. So if we assume the temperature variation is not big enough, it always say it's small enough, then assuming constant specific heat is reasonable. So with these three conditions, ideal gas, this is an isentropic process, and small temperature variation, which means constant specific heat. So we have PV to K is a constant. So we substitute this to this integration, then we should be able to come up with this. Okay, so we could try. Reversible steady flow work is VdP. Now PV to K is a constant, right? So V is constant over P 1 over K, or let's say this is a constant 1 over K times P to minus 1 over K, right? Because P is down here. Okay, so the reversible steady flow work is constant 1 over K integration P to minus 1 over K dP. Okay, so we have this constant 1 over K, then minus 1 over K plus 1, P minus 1 over K plus 1, then from P1 to P2, right? So this is 1 minus 1 over K, constant 1 over K, then this is P2, 1 minus 1 over K minus P1, 1 minus 1 over K. Okay, all right. But we know this, so this constant can be P1, V1 to K, can be P2, V2 to K. This is a constant. Okay, so constant to 1 over K, this should be P2, 1 over K, V2. This is P1, 1 over K, V1, right? I have this exponent. Okay. So this is just times K on both sides. So this is K minus 1 and K. Then P2, 1 minus 1 over K times constant 1 over K minus P1, 1 minus 1 over K constant 1 over K. Okay. Then this constant, I use P2 1 over K V2. And this guy can be substituted by P1 to 1 over K and V1, right? So this is K minus 1. Up here, this is just K. Then we have 1 over K, 1 over K, 1 over K, 1 over K. So this is P2, V2 minus P1, V1. Okay. And don't forget, this is the ideal gas. So PV equals RT. So this is K minus 1, K. This is RT2 minus RT1. So we can move R out here, K RT2 minus T1 over K minus 1. Okay, which is this. Right? Okay. All right. Then how does it become this guy? That's easy. Let me show you. Okay. So we can further do this. K minus 1, K R, and I make T1 here, then the rest should be T2 over T1 minus 1. Okay. And we know PV equals RT. So P1 V1 over T1 should be the same as P2 V2 over T2, right? So T2 over T1 is P2 V2 over P1 V1. Okay. And PV K is constant. So P1 V1 to K is the same as P2 V2 to K. So V2 over V1 to K, this is P1 over P2. Okay, so that means V2 over V1 is P1 over P2 to 1 minus K. So put this here. So this is P2 over P1, and V2 over V1 is P1, P2, 1 minus K, or this is a P2, P1. I want to make this P2, P1 as well. But because we make it upside down, so the exponent should be times a negative sign. Okay. So that becomes P2, P1. This is 1, right? This is 1. So 1 minus 1 over K. Okay. So we put this back to here. Okay. So that becomes K minus 1, K R T1, then T2 over T1. T2 over T1 is this. 1 minus 1 over K minus 1. Okay. This is this guy. Okay. And for polytropic process, for polytropic means PV to N is a constant. So everything else will be the same, except we can replace K with N in this case. So you can see they are the same, exactly the same, except this is a K, this is N, this is a K, this is N, this is a K, this is N, this is K, this is N. Okay, so they are the same. Okay. For isothermal process, it's even easier, okay, because T is a constant. Isothermal means T is a constant. So this is a PV is a constant. So all you need to do is substitute, no, you need to perform the integration directly because that would yield a nature log. Okay. All right. So this is the minimizing the compressor work. And I know these equations are complicated. So in general, as far as I can remember, this happens to the final exam. I would say this happened to the final exam before, but we gave these equations. We gave these necessary equations. I mean, I cannot even remember this. So how do I expect you to remember this? Okay. So don't worry, but I just want to let you know how to get these equations in case it's not guaranteed, but in case you need to derive these equations. Okay. All right. Parfit, my okay, thank you. And okay, so we know the isothermal compression is involves the maximum cooling. However, isothermal compression is very, very difficult to be achieved. So instead, we use so-called multi-stage compression. Multi-stage compression with intercooling. Okay, so what does this mean? Okay, so we know isothermal cooling is difficult. So, but at least we can use polytropic cooling. But we want to maximize the polytropic cooling. So we cool in one stage here. And in another stage, we keep the pressure constant a little bit. So, and at this point, we cool this, we continue the cooling like this. So it's like, let's see, it's like, okay, so this is pressure, this is pressure, this is P1, this is P2. If this is maximum cooling, this is isothermal cooling, and this is polytropic cooling. This is, well, that's iso T, let's say just iso T, okay. Okay, so the idea of intercooling is, okay, so we cool the device using polytropic cooling in first stage. So this is the cooling process. Okay. Then keep the pressure at a certain point. Okay. Then I cool your device from this intermediate pressure all the way to the final pressure you need. So this part is essentially the same as this part. Okay, but we do kind of a shift. We do kind of shift here. So that, okay, if your cooling process is this, we do just one stage cooling, then this area is the work input, right? But if we do this intercooling, then the work required is this area. Okay. So the saved work is let's just use this pink. This area is the energy we saved when we use the interstage or intercooling instead of one stage cooling. Okay, that is the idea. Okay. So this is the work saved. Okay. So you can see that the pressure, this intermediate pressure is important. Okay. If this pressure is too high, then you can see this area becomes smaller. Okay. But if this pressure is too low, then this area will be smaller as well, right? Because if the pressure is high, then your intercooling will go to this. Then this is the area you saved. If the pressure is too low, then this area is the work you saved. Okay, so we want to find out the maximum area or the maximum work we can save using this kind of two-stage cooling. Okay, so to do that, first we need to know the work we saved, the amount of the work we saved. But this is intercooling, so this is what we know from the previous equations, right? So we have two-stage cooling. So this is one stage, this is another one stage. So we want to minimize the work input. So we want to find out what this intermediate pressure is. So the way to do that is we take the derivative with respect to px and setting this to 0. So we can find out what px is. Okay, so you could perform this derivative at home, try to do that, and this is the conclusion. So px, when px is square root p1 times p2, then your work input is minimized. Okay, that is the conclusion. And this problem happened before in the exam, so I would just recommend you to keep this in mind. Okay. All right. So this example is just some kind of substitutions. So substitute K, substitute N, or substitute, yeah, N into different kind of equations we talked about. One is this guy. The other one is like either of, or I think both of these two equations. All you need to do is just do the substitutions. Okay, so I will skip this, and you could compare the work input, work required you get by substituting all these given numbers. Okay. All right. Next is another, I would say another important and different topic, which is isentropic efficiency. And this is a very important topic in chapter 7. So you know what I mean, right? Okay. So isentropic efficiency of steady flow devices. Okay, first, two conditions have to be satisfied to serve as an idealized devices, which is adiabatic and isentropic. So we have these two conditions, not just isentropic alone, because we know theoretically, if your process is reversible and adiabatic, it's necessary to be isentropic. But the other way around may not be true. I mean, if your process is isentropic, your process is not necessary to be reversible and adiabatic, right? Because you have so many combinations, pressure, temperature, things like this to make the entropy the same. Okay, so yeah, so you need to satisfy, your device has to satisfy these two conditions to make your device idealized. Okay, to make your device the best. Okay, so isentropic efficiency or adiabatic efficiency. So you can see isentropic and adiabatic, they are in the same level because they are the conditions that are required to make the device ideal. Okay, so isentropic efficiency or adiabatic efficiency is a measure of the deviation of actual processes from the corresponding idealized processes. Okay. All right. So it's simple. But there are some concepts you need to know. First is efficiency. Remember in chapter 6, when we talked about efficiency and COP, what's the difference between these two? These two index, they are used to evaluate the performance of the device, okay? So usually efficiency, the maximum efficiency is 1, right? So efficiency should be smaller than 1 or smaller or equal to 100%, which is a 1, right? But in refrigerator or heat pump, things like this, because their efficiency is larger than 1, so we would not use efficiency to represent the performance of COP or refrigerator. Instead, we use COP, right? So COP can be greater than 1. Okay, so here it's the same. It's isentropic efficiency, so it has to be smaller than 1. Okay, so so we know efficiency is something over another thing, right? This is smaller than 1. So that means this guy down here, I'll say this is A, it's B over A, right? Smaller than 1. So you need to know that, so B has to be smaller than or equal to A. Okay. So I'm mentioning this because the isentropic efficiency for turbine and pump is different, and it's just upside down. Okay, so keep in mind that the purpose of pump and turbine. So let's say the turbine. The purpose of turbine is what? We want to produce work output, right? And the so-called ideal turbine produce the maximum output, right? Ideal turbine, the output is maximum, right? So the isentropic efficiency should be the work output when the device is actual device over when the device is isentropic. So that this is smaller than 1, right? Because this so-called ideal turbine means it's isentropic turbine. And for an isentropic turbine, its work output is supposed to be the maximum than its actual turbine. So the isentropic efficiency should be the actual work output over the isentropic work output, because in that way, we can ensure the efficiency is smaller than 1. Okay, but for pump or compressor, it consumes work. Right? So it requires work input. So an ideal pump or compressor, work input is minimum, right? So the isentropic efficiency for pump or compressor should be work input, then work is minimum. So the up here, this should be isentropic. Down here, this should be actual, right? Because all actual work input for an actual turbine, an actual pump or compressor should be larger than when this pump works isentropically, right? So that we can ensure this is smaller than 1. Okay, so it's just upside down between turbine, and pump or compressor. So isentropic efficiency, it's a measure of deviation of actual processes from the corresponding idealized processes. And you need to know that efficiency, it's an efficiency. So this guy has to be smaller or equal than 1. Okay. So isentropic efficiency, this is the something over something, right? And let's say this is A and this is B, and this has to be smaller than or equal to 1. So that tells us that A has to be smaller than or equal to B. Okay. So then you need to know for different devices, steady flow devices. We have learned like 7 steady flow devices, right? But here we will be focusing on turbine, pump, diffuser, nozzle, things like this. Okay, so different devices, they are, of course, the definition of the isentropic efficiency is the same, but mathematically, you need to know that the you need to put the isentropic stuff in A or in B. Okay, like for example, for a turbine, if this is a turbine, okay, we know the turbine, we want to maximize the turbine output. So for a so-called idealized turbine, the work output should be maximum when compared to an corresponding actual turbine. Okay, so the efficiency, isentropic efficiency, this should be the work output over another work output. Okay, so because this guy has to be smaller than or equal to 1, so we know when this turbine is isentropic and adiabatic, then the work output is maximum, right? So because it has a maximum work output, so the isentropic work output should be down here. Okay. Then up here, this should be the actual work output, right? Because this is because we know when the work output for an idealized, for an adiabatic and isentropic turbine, the work output is maximum. So this guy is always greater than the actual work output of the turbine. So A stands for actual, S stands for isentropic. Okay, so we know this. So, and we know this. Okay. So the actual work output of a turbine should be up here. The isentropic work output of a turbine should be down here. Okay. However, for a pump or compressor, a pump requires work input, right? So we know when the pump is isentropic or when the compressor is isentropic, then the work input is minimum. Okay, so work input for isentropic pump is smaller than the actual work input of a turbine, of an actual turbine. Okay, and we know isentropic efficiency has to be smaller than 1. Okay, so we can like conclude that isentropic efficiency should be work input isentropic over work input actual. Okay, so this is for pump. Okay, so it's just like upside down when you compare with the turbine, right? Okay, see the actual is up here, but for turbine, the actual one is down here. Okay, so it's different. So similarly for nozzle and diffuser, you can not define, but at least you don't need to memorize because you don't need to memorize the isentropic efficiency for turbine, for pump. See, the actual work is up here, the isentropic work is down here or something or upside down. Okay, because there's a logic to follow. Okay. All right. So yeah, so isentropic efficiency for turbine is the actual work output over isentropic work output because isentropic work output is larger than the actual work output. Okay, so you need to know what this device is used for. Okay, turbine is used to produce power, so we want to have like maximize the power output. Okay. All right. And another point, very important point, is you need to know that okay. So what does it mean when you want to get the so-called actual work output or isentropic work output? Okay. If this is a turbine, this is a turbine. Let's say this is the actual one. This is isentropic one. Okay, there's a work output, work out actual. This is work out isentropic. Okay. All right, then we have inlet, outlet, of course, one inlet and one outlet. Okay. So usually you need to keep this in mind. Usually the inlet conditions are given or are none. Okay, usually the inlet conditions are given or none. Okay. And for actual, now for actual one, of course, is actual, but for isentropic, let's try to use this, like outlet conditions. Outlet conditions. Let me think about how to express this outlet conditions. Actual one is actual, okay, nonsense. Well, it makes sense, but I mean, writing this is nonsense. Isentropic. Okay, isentropic, this means S outlet is the same as S inlet. Okay. So the efficiency for turbine, this is work output actual over work out isentropic. Then we know the work out is the mass flow rate times the enthalpy difference between the inlet and outlet, right? So this is mass flow rate times H in minus H out, right? And down here, this is m dot H in minus H out. Okay. But now we have H in, H out. So when you are dealing with the actual turbine, the outlet, this is actual one, of course. And when you are dealing with the isentropic turbine, and H out is when the entropy is the same as the entropy at the inlet. Okay. But here I want to emphasize that we don't change when you are working on, let me write this, when you are working on the isentropic efficiency, we don't change the inlet conditions. We don't change the inlet conditions. Okay. Okay. That's why here we change only outlet conditions. Okay. So the mass flow rate is the same, and inlet conditions is the same. So inlet conditions are the same. So H in is the same. Okay, in these two cases. Okay. Okay. So I think I don't need to make two schematics. I think I should keep just one. Okay. So the workout depends on the outlet conditions. So outlet conditions, we have actual condition, we have isentropic condition. Okay. Inlet conditions are the same. Okay. So we just change the outlet conditions. Okay. So that's very important point. Okay. We only change the outlet conditions depending on what kind of situation you are dealing with, actual condition or isentropic condition. Okay, so we keep the inlet conditions constant or the same. Okay. Okay. All right. So that's why this is H1. H1 is 1 is inlet in this case. So 1 means inlet, 2 means outlet. Okay, so you can see this is H1, they are the same. But the outlet condition, H2A is the enthalpy at the outlet at actual conditions. H2S is the outlet conditions when this device works isentropically. Okay. And here, this is close. This is close because the kinetic energy and potential energies are negligible. Usually they are negligible, right? Okay. All right. But again, if the kinetic energy, if the velocity or if the elevation are given, you need to take that into account because the efficiency, isentropic efficiency for turbine is the ratio of the actual work output over isentropic work output. Okay, so it's all about the work output. Okay, so depending on if the kinetic energy or potential energy can be neglected, then you should be able to know if you need to take these two energies into account. Okay, but usually no. So that's why here this is just a curves, not an equal. Okay. All right. On a HS diagram, which is model diagram, right? So you can see that we know that if we go back to model diagram, just want to remind you what model diagram is. Where's that? Model diagram, yeah. Okay. So delta H is a measure of work. Delta S is a measure of irreversibility. So you can see if the process is a vertical straight line perpendicular to S-axis, that means delta S is 0. That means it's isentropic, right? So it's isentropic, so delta H, which is the measure of work, is maximum, right? So it's like So this is like this is point one, state one, which is inlet state. It's like a point, a fixed point, and this process curve is a rope, things like this. So this rope is, it's like a pendulum, right? So at point one is a point, so it doesn't move. So point two is moving depending on how many or how much of the irreversibilities this device has. Okay, so it's like this. Okay, so when it's I don't know, this is upright position, then delta H is maximum, delta S is minimum, right? Okay. Okay. So this is the actual outlet condition 2A, okay? So that the curve is slightly off from the vertical one, okay? This is just slight off, okay? All right, so when the process curve on a molar diagram is a vertical line, then that means your device is isentropic, so your device produces maximum work. Okay. All right. So we can look at this, a very straightforward example. Steam enters an adiabatic turbine steadily at 3 megapower, 400 degrees, and leaves at 50 kilopower and 100 degrees. If the power output of the turbine is 2 megawatts, determine the isentropic efficiency of the turbine and the mass flow rate of the steam flowing through the turbine. Okay. All right. Inlet conditions are given, outlet conditions are given, and work output is given. Then we are looking for the isentropic efficiency. Okay. All right. Here, there's another thing you need to keep in mind. Okay. You really need to keep in mind, but let's talk about this later. Okay. This turbine, it produces 2 megawatts work out, and inlet condition 3 megapower, 400 degrees. The outlet condition is 50 kilopower and 100 degrees. Okay. All right. So keep this in mind. So a lot of stuff you need to keep in mind that, of course, all these given conditions, they are real. They are real, of course. Okay. But now, because it's looking for the isentropic efficiency, so you need to consider the outlet conditions to be isentropic. Okay, so this one is the work output, the actual work output. So we are looking for the work output when this turbine is isentropic. Okay, it's adiabatic. This is adiabatic turbine. So as long as this turbine works isentropically, then the work output is maximum. Okay. So how do we get this? Okay. Well, okay. So the first work output, sorry, the actual work output, this is given. So we are looking for the work output when the turbine works isentropically. So this is H1 minus H2S, right? We don't change the inlet conditions, okay? So the inlet conditions are given, so we can get H1 or H in, whatever, okay? But how about H2S? So we want to get H2S, and we know if this turbine works isentropically, that means the entropy at the outlet should be the same as the entropy at the inlet. Okay, so S2 equals S1, no problem, right? You can get S1. So you can get H1 S1 from the steam tables. Okay, and for H2S, we know the entropy, the outlet entropy is the same as the inlet entropy. Okay, but this is only one condition. What is another one? Okay, another one is we keep the pressure the same. We keep the pressure the same. Okay, that is another thing you need to keep in mind. Okay, as long as the temperature and pressure are both given, then you need to do this. You need to use the pressure. You need to keep the pressure. Okay, pressure is the same. Okay. Okay. So as long as you know this, you should be able to get H2S from the table, from the steam table. Okay. So the isentropic efficiency is the workout over workout. Okay. But when this is a turbine, so when turbine works isentropically, the work output is maximum. So it should be down here. The actual one is up here. Okay. Okay. So you can get this. This is H1 minus H2A over H1 minus H2S. Okay. Once again, we don't change the inlet condition. Okay. So the enthalpy at the inlet is the same. Okay. All right. And next part is it's asking for the mass flow rate. Well, the mass flow rate. Okay. So another thing you need to keep in mind is, okay, so mass flow rate is actual mass flow rate or isentropic mass flow rate. Let me tell you, everything as in the question should be actual. Okay, so this should be the actual mass flow rate. Okay, everything that is asked in the question is actual. Okay, so this has to be actual mass flow rate. So the actual mass flow rate is easy, right? Because the actual work output 2 megawatts is given. So you know this is the mass flow rate times the enthalpy difference. Okay, that's it. You have this, you have H1, you have H2A. Okay, so this is H2A, because these are the actual outlet conditions. Okay, so according to the pressure, according to the temperature, you can get the enthalpy from the steam table, and this is the actual one. Okay. So you can get the mass flow rate easily. Okay. All right. We got a question. Why we use the same pressure? Okay. Well, I think this is like the reality. Usually keeping pressure is easier. It's much easier. Okay. So that is the reason. Okay. So yeah, especially in chapter 6 and chapter 7, there are a lot of problems. When you are working on the homework problems, you might need some background knowledge. Okay. And usually you don't. And even me, I don't have so many background knowledge. Okay. So I would say not just to believe the solutions, but I mean, the point is the concepts. Okay, concepts are the most important. Okay, so you don't need to like you don't need to, I don't know, struggling in, okay, why do we need to use the same pressure? Why do we use the same temperature? Things like this. Okay, so because you know, yeah, in engineering stuff, in real world, having a steam table or keeping the steam table, keeping the pressure at the outlet is usually easier. Things like this. No, no. If you use the same temperature, you will get different answers. Okay. You will get. Okay. So you need to use the same pressure. Okay. Yeah, it bothers me a lot, and but that's the reality. Okay. So yeah. Okay. Any other questions about this? No. Okay. For pumps and compressors, the isentropic efficiency is defined by the actual, the isentropic work input over the actual work input. Okay, so this is work input. Okay, this is of course its work input. Okay, so the isentropic work input is minimum. It's minimum, so it's up here. Okay, that's why we can ensure that this efficiency is smaller than or equal to 1. It's not going to be equal, right? But smaller than 1. Okay. Okay. And once again, we don't change inlet conditions. So H1, H1, they are the same. Okay. But H2S is when the outlet condition, when one of the outlet conditions is the same entropy as the inlet. Okay. H2A is the actual enthalpy at the outlet. Okay. So it's the same. Okay. But of course, if you use H1 minus H2S over H1 minus H2A, you will get the same answer, right? Because it's just a minus here, okay? But writing like this is, I think it's like you never learned thermodynamics, okay? Because we know compressor and pumps, they like transfer the work input, they transfer some energy to the working fluid, okay? So the outlet, the energy of the working fluid at outlet should be higher than the energy of the working fluid at the inlet. Okay, so if we want to keep your value positive, you need to use the outlet enthalpy minus the inlet enthalpy. Okay, all right. And for a pump, the the isentropic work input is V delta P, right? Remember the steady, the reversible steady flow work, this, the compressor work is V dP, okay? So in case V is a constant, then that becomes V delta P, right? If V is a constant, okay? Yeah, reversible steady flow work, V is constant. Okay. Okay, it's reversible steady flow work. So if the compressor is adiabatic, then that means it's isentropic. Okay, so that makes sense, right? Because isentropic efficiency is when your device is adiabatic and isentropic. Okay, so reversible plus adiabatic has to be isentropic, but isentropic is not necessarily to be adiabatic and reversible. So we need to combine these two conditions. Okay. Okay. This example, air is compressed by an adiabatic compressor from 100 kilopascal and 12 degrees to a pressure of 800 kilopascal at a steady rate of 0.2 kilograms per second. If the isentropic efficiency of the turbine is 80%, determine the exit temperature of air. Okay, one more time. It should be actual exit temperature. Everything that is asked in the question should be actual. Okay, and the required power input to the compressor. So this is actual. Okay. Okay. The isentropic efficiency is 80%. So this is 0.8. And we know this is work input, the isentropic one over the actual work input, right? Because the isentropic work input is minimum. So it's smaller, So to ensure the efficiency is less than 1, the smaller one, the smaller value should be up here, okay? And it should be H2 minus H1, H2 minus H1. Okay, this is S and this is actual. Once again, we don't change the inlet conditions. Okay. Okay. Then inlet conditions are given, so we can get H1. Okay. So outlet condition, okay. So we have H1 and S1, okay. So S2 equals S1. So with these two, we can have H2S, okay. So we have H1, we have H1, we have H2S. So from this, we can get H2A. Okay. So with H2A and P2, which is 800 kilopar, we can get T2, actual one, and the actual power input. Actual power input is the mass flow rate times 2 H2A minus H1. Mass flow rate is given. Okay, so this is the actual work input. Okay, all you need to do is to find out what is H, what is S from the steam table, no, from ideal gas tables. Okay. Well, let me see. No. There's something wrong because this is air, so we are unable to get S. Okay. We are unable to get S. Okay. So no, you cannot find S directly. Okay. Because this is air. We know the properties of air. Many of the properties of the air are functions of temperature only. Okay. So yes, we can get H1. Okay. But for temperature, no. You need to apply S2 minus S1. This is what? This is CV average. We know this is CV average natural log temperature ratio. I think this is plus R natural log V2 over V1 over CP average natural log T2 T1 minus R natural log P2 P1, right? We have these two equations, right? And this is 0, okay? This is 0. So we want to use this because P2 is given. Because P2 is given. P1 is given. So this is 0, then we should be able to get T2, right? R is 0.287, right? P2, P1, they are given, and CP average, okay, CP average is unknown, but you could use CP at T1, which is 285K. Okay, so you have a value this, then you get a T2. You get a T2. Okay. So you get a T2, then you need to go back to double check if assuming CP average is CP at T1K, is CP at T1 is, you need to check is assuming this is reasonable by comparing, CP at 285K to see if this is close to T1 and T2 average. So because you got a T2 here. Okay, you need to check if this is reasonable. Okay. So once you have T2, this is T2. Hold on. Yeah, this is T2S. This is T2S, right? Because we assume this is 0. So once you have T2S, then you should be able to get H2S because enthalpy of air depends on temperature. So once you know the temperature, you should be able to get H2S from the table. Okay, so you have H2S, you have H1, so you can get H2A. Okay. Yeah, so you have H2A, then you can get T2A from the same table, right? You know enthalpy, you know temperature for air. Okay. Okay. Questions for this? It's not reasonable, then you need to do another guess. Okay. Usually this is how we do. Okay, let me write this. So now if you assume CP is 285K, then you have a T2. Okay, so you need to check if CP at 285K is close enough with CP at T2, T1, T1 average. If no, then you need to assume CP. Usually I would do this. I would do CP at T2, T1 average. I just do the average. Then you will get a new T2, right? Then repeat. I would say repeat. If CP at T2 plus T1 over 2 is close enough to CP at new T2. Okay. If no, then you just do the iteration like this. Okay. It's guess. Okay. But usually in the exam, we would not let you to do that. Okay, to do this kind of iteration. Usually we would tell you that just assume CP is a constant at what temperature. Okay, things like this. Let me check the text for this example. Okay. This is isentropic efficiency for pump. Okay. And okay. Okay, so the textbook uses different method. Okay. Okay. It's a different method and it's important. It's also important, useful, and it's exact. Okay. It's that don't forget for isentropic process, for ideal gas undergoing isentropic process, Let me go here. Okay, so this is what we just used. Okay, right? Use the average one. Okay, but yeah, there might be a problem if you don't have one of the temperatures. So you have difficulty to get this. One way to do that is what I just did. I assume CP is at a certain temperature, then I do iteration. Another way to do that is, let me see. Yes, don't forget these three useful equations. Okay. And this is a constant specific heat. Okay, here. Variable specific heat. Okay. Don't forget this. Variable specific heat, which is exact for isentropic process of ideal gases. Okay. We have 1 and 2. Okay. So in this example, for isentropic air compressor, the pressures are given. So pressure ratio is the same as the relative pressure ratio. Okay. And relative pressure is function of temperature only. Okay, so you know this ratio, right? This is 100 over 800. And you can get PR1. You can get PR1 because T1 is given. So you should be able to get PR2. Once you have PR2, you should know T2 as. Okay, that's another way to go. And this is exact because you don't need to worry about the iteration. Okay. Okay. So in the textbook, it uses another exact method to get the temperature for when the process is isentropic. Okay, so let me see T. This is air compressor. Okay, air is ideal gas. So we have well, the question doesn't state that we need to use the variable specific heat, or we can assume the specific heat constant. Okay, but to be conservative, we assume the specific heat varies with temperature. Okay, so in this case, for ideal gas, isentropic isentropic process, then we know the pressure ratio is the same as the relative pressure ratio. Okay, and we know relative pressure is function of temperature for ideal gas. Okay. So in this case, we have P1, 100 kilopascal, P2, 800 kilopascal. Then we can get PR1 because T1 is given. This is T1. T1 is given. So So we have, you can get PR1 from the table. So that means you can get PR2 because of this relation, okay? So once you have TR2, then you have T2. And this T2 is when the process is isentropic, right? Because this relation is established based on the isentropic process, okay? So this T2 has to be isentropic T2, okay? So going back here, so you have T2, then you can get H2 S, of course. So from this given condition, then you can get H2A. So you have H2A, then you can get T2A, okay, because this is air. Okay, enthalpy depends on temperature only, so you can get T2A. Okay, then the work input, the actual work input is H2A minus H1 times the mass flow rate, which is given. Okay, so that works, of course. Okay, but in case if the problem tells you you could assume constant specific heat, then you can do this. You can do the iteration, of course, but like I said, usually we would not let you to do that. Usually we would give you, you can assume the specific heat at a certain temperature. Okay, that would be much easier. Okay. Next, isentropic efficiency of nozzles. And I believe this is diffusers. No, just nozzles. Okay. Well, for nozzle, it's okay. But because the nozzle doesn't produce or consume power, so the definition of the isentropic efficiency of a nozzle is function of kinetic energy. So the actual kinetic energy and isentropic kinetic energy. Okay, for nozzle, we know for a nozzle, a nozzle is used to increase the velocity of the gas or the velocity of the working fluid. Let's say this. Okay, so the kinetic energy at the we want to like maximize the kinetic energy for a nozzle, right? Because the kinetic energy is a function of the velocity. So if we if we want to maximize the velocity, that means we want to maximize the kinetic energy. Okay, so the kinetic energy is down here. The actual kinetic energy is up here. So this is actual, this is isentropic. Okay, and don't forget there's a square here. Okay, right? Because the kinetic energy is actually 1/2 m dot v square. Okay, m dot is the same. It's a mass flow rate, and it doesn't change, right? Usually a nozzle or diffuser, they have like one inlet and one outlet. So the mass flow rate is the same. So we don't need to worry about this 1/2. We don't need to worry about the mass flow rate. All we need to take care is the velocity square. Okay, so don't forget there's a square here. Okay. Okay. And it's H1 minus H2. Okay, of course. Okay. So for if a so-called idealized nozzle, that means it's adiabatic, and of course it doesn't produce work, or it doesn't require work input, and we assume the potential energy is negligible. Okay, so this is the remaining the enthalpy change. So it's enthalpy change, right? If just want to remind you, the energy balance equation for steady flow devices is like this, right? So E in dot and E out dot, this is the mass flow rate, right? The mass flow rate in times H in plus 2V in square minus M out dot H out plus 2V out square. This is 0. And the mass flow rate at inlet and outlet is the same, right? Mass conservation. So this the kinetic energy change is the same as the enthalpy change. Of course, there's a 2 here, but because there's a 2 here, up here, there's another 2 down here. So 2 doesn't matter here. Okay. So the remaining is the enthalpy change. Okay. And once again, we don't change the inlet condition. So H1, H1, they are the same. We change only outlet conditions. Okay. From the actual conditions to isentropic conditions. Okay. Okay. So another note that the exit pressure is the same for both actual process, but the exit state is different. So this, we mentioned this, we keep the pressure the same. We keep the pressure the same, okay? All right. Let's try this example. It's air nozzle and looks like the isentropic efficiency is given. Inlet conditions are given, pressure, temperature, and we assume V2 is much greater than V1, okay? And P2 is given. So we are looking for the maximum possible exit velocity and the exit velocity. So this should be actual one, actual exit velocity and actual exit velocity of the air. Sorry, this is actual exit temperature, actual exit temperature. Okay, possible. Assume, okay, assume constant specific heat for air. That's nice, right? Because that means it's ideal gas. If the process is isentropic, then we have 3 sets of equation, right? Which is PV to K is constant, PB K minus 1 is constant, PT to function of K, whatever, is a constant. Okay. Okay. So part A is looking for the maximum possible exit velocity. Okay. Maximum possible exit velocity. This happens when the nozzle is isentropic, right? It's already adiabatic. So as long as this nozzle is isentropic, then the exit velocity would be maximum. Okay. So let me use this. This is a nozzle. Isentropic efficiency. Outlet pressure. Okay. So maximum possible velocity. So we know the isentropic efficiency of a nozzle. It should be V2 square over V2 square. Okay. So the isentropic efficiency, isentropic velocity is bigger than the actual one, right? And we know this is a nozzle. So nozzle, this is H, should be what? H2 minus H1. H2 minus H1. This is 2A, this is 2S, because we don't change the inlet conditions. To me, just double check. No, H1 minus H2. Sorry. Well, it doesn't affect numerical stuff, but we need to make it right. Just like we are learning thermodynamics. Okay. Okay. Okay, then how do we do that? Okay. We know this is air. So the enthalpy of air depends on temperature only. Okay. So we can get H1, of course, and this is 0.92. So we can get H2, right? Because P, this is pressure, temperature, this is pressure. So for ideal gas, isentropic process, and constant specific heat, then we know we have Tp, I think it's Tp, 1 minus K over K is a constant. Go, let me check. I have a few summaries at the end of the handout. This is summary. Yeah, there we go here. Tp 1 minus K over K. Tp 1 minus K over K is a constant. So T1, P1, 1 minus K over K is T2, P2, 1 minus K over K. So this is air, and K is, I think it's 1.4. Check K. For air, let me go back. Okay, we probably don't use that. Okay. Of course, it's one way to go, but now you can see, because the specific heat K, the specific heat ratio is a function of temperature as well. Okay, so we don't use this. Instead, we use the same technique, the pressure ratio. Is PR1 over PR2. Okay, so pressure ratio P1 is 200, P2 is 80, and you can get PR1 because P1 is given. Wait, this is when Hold on. Constant specific heat. Okay, that's not good. Okay, because the question is asking us to assume the specific heats are constant. So yeah, we cannot use this because this pressure ratio or the relative pressure ratio or relative specific volume ratio is for variable specific heat. Okay, so looks like we need to stick with this. Okay, but let me see. Okay, yes. Now the textbook guesses that K is assumed. It's assumed at an average value. Okay. So I would say we assume K at, I don't know, 300K, 1.4. It assume, okay, so it assume the temperature drops. Okay, so we can imagine temperature is lower than the outlet temperature is lower than the inlet temperature. So here, the textbook makes an assumption that K is at 800K. Okay, because inlet temperature 950K, and we know the outlet temperature should be lower than the inlet temperature. So it makes an average like K at T1 over T2. And here we assume it's 800K. Then that means you need to perform the iteration, just like what we did for the last example. Okay. So you have 800K, so the specific heat ratio can be found in the table. Okay. So T1, P1, and P2 they are given. So T2, you can get T2, right? You can get T2. And this T2 is when the process is isentropic. So this is T2S. Okay. So once you have T2S, you can get H2S because it's air. So the enthalpy depends on temperature only. Okay. So you can get H2S. Okay. So you can get H2A. Okay. And what is asking? The actual temperature, exit temperature. You have H2A, then you should be able to get T2A. This is a part A. No, this is a part B. Okay. Then we are looking for the maximum possible exit velocity and actual exit velocity. Okay. So you have H2A, you have H2S, then you know that 1 over 2 m dot V2 square is m dot H1 minus H2. Okay, so yeah, So 1/2 m dot, we have m dot, we have m dot, we have m dot. So 1/2 V2A square, this is H1 minus H2A, 1/2 V2S square, it's H1 minus H2S. Okay, so V2S is the maximum possible exit velocity when this nozzle works isentropically. Okay, of course, then this is V2A. Okay. But here I want to remind you that because the enthalpy given in the table, if you go to A17, H given in the table is kg per kilogram. Okay, this is kg per kilogram. But when you are calculating the velocity, because there's a square here, so you need to take a square root, something like this. Don't forget this k. This k is 1000, right? If you have, for example, like if V2 square is, just for example, 200 kg, kg, then if you make, let's say 400, that's easier, okay, square. So V2, if you say this is 20 meter per second, then that would be so wrong, right? Because this is kg, so you need to take this like square root 400 times 1000, okay, to make this joule per kilogram. Okay, so it's not like just square root 400. Okay, should be square root 400,000. So the unit here is meter per second. Okay, just want to remind you. Questions about this? And of course, you need to go back to check if making the average temperature, assuming the average temperature is 800 K, is reasonable. Okay, by checking this T2 or T2, the average between T1 and T2 is close to 800 K. Okay, but if you go back here, you can see, I would say these three values, they are very, very close. So if your average value is between 750 and 900, then you're okay. You assume 800 average temperature between the inlet and outlet is reasonable enough. Okay. Let me check the textbook. The textbook here is T2S. T2S is 748. Okay, so the average between the inlet and outlet this is what? It's around 800, right? No, it's 200, it's 80, at 50 degree K. Okay, so at 50 degree K, it's somewhere, it's in the middle between 1.344, 54, and 44. Okay, so it's supposed to be 1.3 49. It's around this. Okay, but this difference, I mean, using this 1.354 and 1.349, using these two cases would result very similar answers. Okay, so so making this assumption is reasonable enough. Okay. Okay. And so T2A is actually 764. Okay. So you can see the difference between the difference of the temperature at the inlet and outlet. When the process is isentropic, then the temperature difference is larger because we convert the enthalpy difference between the inlet and outlet into the kinetic energy, right? So 95 to 748 delta T, this delta Ts is larger than the actual process. Okay, this is delta T actual. Okay, so this is larger. Delta Ts is larger than delta Ta. So that means when this nozzle works isentropically, it can convert little bit higher enthalpy difference into kinetic energy difference. Okay. All right. Questions about this? No? Okay. Then next, which is the last part in chapter 7. So if you look back the chapter 7, you can see chapter 7 can be divided into 3 parts. Okay. One is like concepts of entropy. Okay, so you need to remember those two essential equations, right? The entropy change of solids, the entropy change solids, liquids, and ideal gases, right? And for ideal gases, we have like constant, then entropy change of, this is general. This is general. And when the process is isentropic, things like this. Okay, so this is part 1. Part 2 is isentropic efficiency, which we just finished. Okay. And the last part is entropy balance. Okay, so 3 parts. I would do that. I would divide chapter 7 into 3 parts. Some important concepts, and isentropic efficiency and entropy balance. I believe in the final exams, every part has some questions popped in the final exams. This is what I believe. Okay. All right. Going back to entropy balance. Okay. Let's see. The second law states that entropy can be created, but it cannot be destroyed because we are making this universe chaotic every day, every moment, every second. Okay. The entropy change of a system during a process is greater than the entropy transfer by an amount equal to the entropy generated during the process. Okay. Remember the entropy increase principle? In an isolated system, the entropy always increases. Okay, even though we know every single or every small system, the entropy change can be positive, can be negative, but like for a system like this, okay, if this system is losing heat, then delta S in this system is smaller than 0, right? Because the entropy decreases. But for this surrounding air, delta S is greater than 0. Okay, because the surroundings receive heat. Okay, so together, like if this is S1, this is S2, together delta S1 plus delta S2 has to be greater than 0, which is entropy generation. Okay, entropy generation of this heat transfer process. Okay, so the entropy change of a system during a process is greater than the entropy transfer by an amount equal to the entropy generated during the process. So in equation, the increase of entropy principle or entropy balance equation is this. It's exactly the same as the energy balance. Okay. So just recall that the energy balance equation is E in minus E out. Let me see. Is delta E system, right? And these two, they are energy transfer mechanisms, right? So energy can be transferred by heat, by work, and by mass, right? The energy change of a system, this is the internal energy change, kinetic energy change, and potential energy change. Okay, this is for energy. The entropy balance it's very, I'll not say exactly the same as the energy balance, but very similar. So there's S in minus S out plus S generation. This is delta S system. Okay. So these two guys, they are entropy transfer. Remember, entropy can be transferred by heat and mass only, okay? Because work is free of entropy. Work doesn't contain entropy. So this is by heat and by mass. Okay. And this is entropy generation. Okay. So entropy transfer by heat and by mass, this is the entropy generation, the entropy change of the system. Okay. Very straightforward equation, very, very similar to energy balance equation. Okay. So yeah, so we have this energy balance and entropy balance. Okay, but look at this. So the entropy change of a system during a process is equal to the net entropy transfer through the system's boundary and the entropy generated within the system. Okay. And you need to know that the entropy generation has to be larger than or equal to 0. When the entropy generation is 0, that means your process is isentropic. Right? Entropy generation is 0. No, I think it's just reversible. If your process is reversible. Then entropy generation. Okay. 0 entropy generation is internally reversible, but not necessarily totally reversible, because we are talking about the system. Okay, so the entropy generation is 0. That means the entropy associated with the process inside the system is 0. So it's just about internally reversible, not necessary to be totally reversible. Okay. So entropy generation represents the entropy generation within the system's boundary only. Okay, within the system or within the system boundary only. Okay. But entropy generation that may occur outside the system boundary. Okay. The total entropy generated during a process can be determined by applying the entropy balance to an extended system. So now question is, what is so-called extended system? Okay, let's see this. Okay, extended system is like a system that includes, let me write. If you have pistons in the device like this, so the extended system is a system that includes these pistons in the device and its immediate surroundings. Okay, so this is extended system. Okay. So it includes your original system, which is pistons in the device in this case, and immediate surroundings. Okay. All right. So you can see this one, this is extended system. Okay, so it includes the surroundings and this original system. Okay, so unlike energy, entropy does not exist in various form. Okay, right? We know we have thermal energy, electrical energy, we have chemical energy, we have so many kinds of energies. Okay, but entropy does not exist in different forms. Entropy is just entropy. The determination of entropy change of a system during a process involves evaluating entropy of the system at the beginning and at the end of the process and taking their difference. So yeah, it's just entropy change. So as long as you can find out what the entropy is from the table, then go ahead to do that. Okay, because this is just entropy is one of the properties. So you can find entropy from the property table. Okay. So that tells us that entropy depends on the state, right? Unless the state changes, the entropy changes. If the state doesn't change, that means the entropy doesn't change. Okay. When the properties of a system are not uniform, the entropy of the system can be determined by integration for. Okay, but we barely use this. Okay, but you need to know if the entropy is not uniform everywhere in the system, then you need to perform the integration to get the entropy. Okay, but we don't use this a lot. Okay. Mechanisms of entropy transfer. We know entropy can be carried by heat and mass because the work is free of entropy. So work is not one of the entropy transfer mechanisms. Okay, so entropy can be transferred by heat and mass. Okay. By heat, heat is a form of disorganized energy, and some disorganization, which is entropy, will flow with heat. Okay, so heat, this is from the very original definition of entropy, right? Entropy is heat over temperature. Okay, but here I want to emphasize that because this is entropy transfer. So just like the energy transfer, so transfer implies that something is acrossing the boundary. Okay, you need to have something across the boundary. In this case, of course, entropy crosses the boundary. Okay, so this entropy carried by heat is Q over T. Q is an energy transfer mechanism, right? Because so Q is crossing the boundary. So T should be the temperature at the boundary. Okay, so this T should be the temperature at the boundary. Okay. Another one is the mass flow. Then because we know the mass carries entropy, so all you need to get is find out what the entropy from the table. Okay, then times the mass. Okay, times the mass. So we know entropy can be transferred by two mechanisms. One is heat, the other one is mass, right? So work is free of entropy, so work is not one of the entropy transfer mechanisms. Okay, so entropy, heat is a form of disorganized entropy. So the entropy transfer by heat is simple. It's just Q over T. Okay, but here there's one thing you can see is Q. So Q is heat transfer. Okay, and what we are talking about is entropy transfer. Okay, so transfer implies that it's a boundary phenomenon, right? So entropy means, transfer means something is crossing the boundary. So if this is the boundary of the system, okay, so something is crossing the boundary. So entropy transfer means this entropy is crossing the boundary. Q is the same, right? Heat transfer means there's a heat crossing the boundary. Okay, so this is a transfer implies it's a boundary phenomenon. Something is crossing the boundary. So T here, this T means the boundary temperature. This is T. Okay, so T is boundary temperature. This is a boundary temperature. Okay, because heat transfer is a boundary phenomenon, so the temperature we need to use in entropy transfer here should be the boundary's temperature. Okay, that's the entropy transfer by heat. The entropy transfer by mass, this is simple because this S is just the entropy of that mass at a specific state. Okay, so in general, this S is from the table. Okay, at a specific state because we know entropy. Entropy is a property. Okay. Let's say entropy is a property. So the entropy transfer by mass is just the mass times the entropy. Okay, and this guy, you can find this from the table. Okay, so only two entropy transfer mechanisms. Okay. So irreversibilities always cause entropy increase, friction, mixing, chemical reaction, finite temperature difference, heat transfer, expansion, things like this. Okay. So as long as your process is irreversible, then there must be an entropy generation. Okay. So for reversible process, well, reversible process involves no irreversibility, but we know reversible process, it doesn't exist in reality. Okay. So all happening processes are irreversible. Okay. So if your process is reversible, your entropy generation is 0. Okay. All right. So for closed system, that means there's no mass flow. So you don't need to worry about the entropy carried by mass. Okay. For open system, then open system, in this case, in our class, the steady flow is usually assumed for an open for an open system or a control volume. Okay, so if we give a very quick summary about entropy balance. Okay, so entropy balance, just like energy balance, we can write it in two types of format, right? So one is S in minus S out plus entropy generation. This is the entropy change of the system. This is one, right? We can also write this in a rate format. S in dot minus S out dot plus entropy generation rate. This is d as system over dt. Okay, so usually for a closed system, we will use the first one. Okay, but for open system, we will use this the second one, which is in rate format, right? Because if your system is steady, this is for steady open system, steady for device. Okay. These two guys, they are entropy transfer mechanisms. So entropy can be transferred by heat and by mass. Entropy can be transferred by heat and by mass. Okay. Okay. So entropy transfer by heat this is S, which is Q over T over S dot is Q dot over T. Okay. T is the boundary temperature. Okay. T is boundary temperature. Okay. Entropy transfer by mass. S is ms. Okay. This is uppercase S. This is lowercase. Okay. This is from the table. Okay. Or S dot, the same. Uppercase S dot. This is M dot times S. Okay. So these two S, they're the same. Okay. So let's try a few examples. We have only 5 examples in this part. Okay. First one, consider steady heat transfer through a brick wall of a house on a day when the temperature of the outdoors is 0 degrees, the house is maintained at 27 degrees. The temperatures of the inner and outer surfaces of the brick wall are measured to be 20 degrees and 5 degrees. And the rate of heat transfer through the wall is 1035 watts. Determine the rate of entropy generation in the wall and the rate of total entropy generation associated with this heat transfer process. Okay. So first one, we are looking for the entropy generation in the wall, just in the wall. Okay. So this is how we do that. This is how we do this. So we select the entire wall as a system. And this heat transfer process is like this. We can like divide this into 2 processes, but these 2 processes are heat transfer processes and the amount of heat transfer is the same. Okay, so here we have Q, which is 1035. This is another Q, which is 1035 as well. Okay, so this is Q in, this is Q out. Okay, because this heat transfer process is through the entire wall. Okay, all right. So from the entropy balance equation, okay, we know S in dot minus S out dot plus S generation dot is 0 because this is a steady case. Okay. This is steady, right? Well, there's no word steady. Oh yeah, steady. Okay, it's a steady case. So is 0. So this is 0. Okay, because everything that changes over time is 0, which is the definition of steady. Okay. So S generation dot is S out dot minus S in dot. Okay. All right. And in this case, the only one entropy transfer mechanism is heat transfer. Okay. So this would be S out is 1035 over out. Out is here. So this wall, the wall temperature here is 5 degrees. The wall temperature here at the left-hand side is 20 degrees. So this is 1035 over 5 plus 273. Don't forget to use absolute temperature. Okay. Because you know, using degree C and K would be resulting in different results, right? In this case, okay. So minus 1035 over S in dot. This is Q in. So this Q in is across in a 20 degrees wall, okay. So this is 20 plus 230. Yeah, 233. Okay, so this is 1035 over 278 minus 1035 over 283. So this is, oops, is that? 1035 over, okay, 293. So this should be 0.19 watts per degree K. Okay. So this is the entropy generation of the wall, just for the wall. Okay. All right. Then, okay. Then we are looking for the total entropy generation. Okay. Because this heat transfer process, it affects not only the wall, it affects only, it also affects the surroundings of this brick wall. So if whenever the problem asks you to get so-called total entropy generation, you need to do this. You need to select a so-called extended system like this. So this extended system includes the system, in this case, which is brick wall. Brick wall is our original system. And extended system includes the brick wall and the immediate surroundings. So immediate surroundings is the surroundings very close to the system, okay, so that we can count the entropy change of these surroundings by the process, by this specific process, okay. So we can write the entropy balance equation one more time. S in dot minus S out dot plus okay. So for this one, it's pretty much similar to the idea for the first question. but except now this heat transfer is crossing two boundaries that are at indoor temperature and outdoor temperature. Okay, instead of the wall temperature. Okay, so in this case, S in is 1035 over 27 plus 273, which is this. Okay, and S out is 1035 over 0 plus 273 because the outdoor temperature is 0 degrees. Okay, then we can get the entropy generation in this case. Okay, so that would be 1035 over 273 minus 1035 over 300. Okay, so you can see the entropy generation is positive. That means that implies this heat transfer process can really happen. Okay, and the entropy generation in this case is completely because of the finite temperature difference. Okay, because this heat transfer process is resulted from the finite temperature difference, right? This is 27, sorry. This is 27 degrees, the wall temperature is 20 degrees, so there's a heat transfer here. This is 20 degrees, this is 5 degrees, so there's a heat transfer. This is 5 degrees and 0 degrees, so there's a heat transfer. So heat is always from high temperature to low temperature, right? This is from the nature. Okay. All right. Next one, this is a throttling valve. So we are looking for the entropy generation in this throttling process. Okay, so is throttling valve and it's a steady flow device. Okay, so the entropy generation, we can get entropy generation from the entropy balance equation. Okay, it's an open system, it's a steady flow device. So the entropy generation is like this. This is 0 because it's a steady case. Okay. All right. And you can see this throttling process doesn't involve any heat transfer, but there's a mass transfer, right, coming in and out of this system. Okay. So these two should be as mass dots, as mass dot. Okay, so entropy can be transferred by mass in this case because there's no heat transfer involved. Okay, so we know this should be m dot times s. Okay, it's entropy transfer by mass. Okay, so this case, we have m dot in as in, or let's say 1. Inlet is 1. Okay, outlet is 2. So m1 dot s1 minus m2 dot s2 plus s generation dot is 0. Okay, so s generation dot is m2 s2 m2 dot s2 minus m1 dot s1, but m1 dot is the same as m2 dot because in this device there's only one inlet, one outlet. Okay, so I will just drop out the subscript. Okay, but because the mass flow rate is not given, so if I divide the mass flow rate, that would become just S generation, right? So this is just S2 minus S1, okay? And this S, this is from the table. Okay, so all you need to do is just to get what S is. So we have pressure, we have temperature, so you should be able to get S1. This is steam. So just go to steam table to get S1. Okay. And throttling process, the unique characteristic of a throttling process is the enthalpy doesn't change after throttling process, right? So H2 should be the same as H1. Of course, you can get H1, right? Then you have these two properties, so you can get S2 from the steam table as well. So you have S2, you have S1, so you can get the entropy generation. Okay. So the reason to have entropy generation during the throttling process is because of the expansion, right? So this is unrestricted expansion during the throttling process. Okay, is irreversible. Okay. Next one, okay. So this one, we have a very hot ion casting is thrown, yeah, it's thrown into a lake, and eventually this ion casting will be in thermal equilibrium with the lake. That means their temperature will be the same. Okay. Assuming an average specific heat for the ion, and we are looking for the entropy change of the ion block, the entropy change of the lake water, and the entropy generated during this process. Okay, so we know there's a heat loss from this ion block to the lake. Okay, but this is a lake. Okay. So the mass of the lake is supposed to be way larger than the mass of the ion block. Okay, so for the block, the lake can be considered as a thermal reservoir to absorb this energy. Okay, and from the definition of thermal reservoir, the temperature doesn't change, right? The temperature of a reservoir doesn't change, no matter how much energy it absorbs over its supplies, right? So first, we need to know the temperature of the lake doesn't change. That implies that in thermal equilibrium state, the final temperature of the ion should be the same as the lake temperature, right? Which is 285 K. Okay. All right. So we need to come up with these two summaries or conclusions, whatever you want. Okay. But let's look at part A. The entropy change of ion block. So we know ion is, this is an incompressible substance. Okay, so the entropy change of incompressible substance is MC natural log T2 over T1. Remember this? Okay. So this is 50 kilos, which is the mass. C is 0.45 times natural log T2. So T2 is 285. T1 is 500. Okay, so you can get this. And you can see this is a negative value because this is smaller than 1. So natural log smaller, something smaller than 1, it should be negative. Okay. So 50 times 0.45 times natural log 285 over 500. So this is minus 12.65. Okay. It's negative. So, and it makes sense, right? Because the Bragg is losing heat. Okay. So the entropy decreases. Okay. But for the lake, the lake temperature doesn't change. Okay. So in this case, the lake temperature doesn't change, but the lake receives heat from the ion Bragg. Okay. So the entropy change of the lake is just Q over T. Okay. So as long as we can find out what Q is, then we should be able to know the entropy change of the lake. Okay. So how do we get Q? If you take this Bragg as a system, and we know there's a heat loss, then now we need the energy conservation. Okay. For ion Bragg, we need energy conservation. E in dot minus E out dot is delta E system. Okay. So in this case, we have only one energy transfer, which is the heat loss. So there's a minus Q. And this is the system's energy change, which should be the internal energy change, right? Internal energy change is the mass times the specific heat times delta T, okay, which are all given, which is 50 times 0.45 times delta T. So delta T is T2 is 285 minus 500. Okay, so you can get Q, which is a positive quantity. So 5 times 0.45 times 285 minus 500. Okay. So we have the entropy change of the lake, which is positive. So this is positive 16.97. Okay. All right. So this is part B. And part C, the entropy generated during the process, which is just the summation of these two entropy change. Okay. So S generation should be this guy minus this guy. So that will be just 4.32. Okay. That's all. Okay. So in many occasions, we need the entropy energy balance to help us I'll say sometimes yeah. We need to use energy balance to get what? Q over mass flow rate. I'll say Q dot over mass flow rate, things like this. Okay, so mass flow rate Q dot over Q. Especially in steady flow devices, we can use energy balance equation to get this. Okay. Next one. Oh, sorry. So this entropy generation is because of the finite temperature difference, this heat transfer process. Okay, so it happens naturally. Okay. It can happen naturally. Okay. Next one is mixing chamber. Okay, so mixing process is irreversible. Okay, so there must be an entropy generation. Okay, so in this case, we are looking for the entropy generation rate during this mixing process. Okay, so this is water. Okay, we have two inlets, 1, 2. Okay, this is a cold water, this is hot water, and one outlet. This one is warm water. Okay, and that's a heat loss. Okay, we are looking for the total entropy generation. So how do we do this? We are looking for total entropy generation. So all we need to do is to select an extended system. And we apply the entropy balance to this extended system. Okay. So this is a steady flow device. So S in dot minus S out dot plus entropy generation dot is 0. Okay. All right. So S in dot S out dot. So in this case, we have heat transfer, we have mass transfer. Okay. So Q dot is the entropy carried by heat. This one is Q dot over T, right? This one is M dot times entropy. Okay. So in this case, we have 4 entropy transfers, okay, which is M1 dot S1 plus M2 dot S2 minus M3 dot S3 minus Q dot over T surrounding. Okay, so Q dot over T surrounding is because of this. Okay, and the surrounding, we use the surrounding temperature because this system is extended system. So the boundary is the somewhere in the surroundings. Okay. So it should be T surroundings and plus entropy generation is 0. Okay. All right. Then so we have the mass flow rate M1 dot. We can get S1, we can get S2, we can get S3 because the temperature, pressure, they are all given. Okay. However, in this case, this is a liquid water, which is a compressed liquid. Okay. So, and we know we have very limited table for compressed liquid. So practically, we would use the approximation we use approximation to get approximated properties, right? So when the pressure, temperature are given in this case, so S1 should be the saturated liquid point at 50 degree F, right? Remember this. S2 should be saturated liquid point at 240 degree F. S3 is the same. It's saturated liquid at 130 degree F. Okay. So you need to use the table to get this. And this is approximation. Okay. So we have S1, S2, and S3. Q dot is known. The surrounding temperature, 70 degree F, is given. Okay. So now we are still missing M2 dot and M3 dot. Okay. How do we get this? Using energy balance. So to get M2 dot and M3 dot, we need to apply the energy balance. And don't forget, in chapter 5, when we are working on so many steady flow devices, other than the energy balance equation, we also need mass conservation. Okay. So energy balance gives us that E in dot minus E out dot is 0 for steady flow. Another thing is mass conservation. So mass conservation in this case should be M1 dot plus M2 dot is M3 dot, right? This is a mass conservation. Okay. So if we expand the energy balance equation in this case, we should have M1 dot H1 plus M2 dot H2 minus M3 dot H3, then minus Q dot. This is 0. Okay. So we know M1 dot H1, H2, H3 is the same as a way you get the entropy. Instead, now this is H1 is close to HF at 50 degree. H2 is close to HF, which is a saturated liquid point using temperature table 240 degree F. H3, this is the same, HF at 130 degree F. Okay. So you have this. So you have two equations, two unknowns. So you can get M2 dot and M3 dot. Okay. Put this back, then you can get the entropy generation. Okay. Little bit complicated, but still manageable. I often say this, right? Because it requires the knowledge you have learned previously, especially energy balance and mass conservation. Okay. Okay. Energy balance. Sorry. Okay. Okay. So this entropy generation, you need to do the math. You need to do the calculations. So you will see this entropy generation should be a positive value. It has to be positive because mixing is a reversible, it's a irreversible process. Okay. So every irreversible process would generate entropy. Okay, so this has to be a positive one. All right, last one. This is the last one. Okay. This is a frictionless piston cylinder device, contains a saturated liquid vapor mixture of water at 100 degrees. During a constant pressure process, 600 kg of heat is transferred to the surrounding air at 25 degrees. As a result, part of the water vapor contained in the cylinder condenses. Okay. This is interesting. Okay. Because the original state, the initial state, is saturated mixture, okay? And we know if the pressure remains constant for a mixture state, the temperature is a constant, right? This is a phase change process. It's liquid vapor mixture, so it's during like phase change process. For a constant pressure phase change process, the temperature is the same. Okay, so temperature remains 100 degrees. Okay, and just part of the water vapor condenses. That means after this heat losing process or heat rejection process, the final state inside this piston cylinder device is still mixture. So the temperature of the final state should be 100 degrees as well. Okay. So after losing this 600 kg of heat, the system's temperature is still 100 degrees. Okay. So you need to be aware of this. Okay. So now we are looking for part A, we are looking for the entropy change of the water. Okay. Now it should be straightforward because you know the temperature of the water remains constant during this heat rejection process. Okay. So delta S water is 600 over 100 plus 273. Okay. So this is, it should be minus. Okay, because this is a heat rejection process. So this water is losing heat. So the entropy should decrease. Okay, so this should be a minus. Okay. Part B, the total entropy generation during this heat transfer process. Okay. So the water is losing heat, so the entropy should decrease. However, for the surrounding, it's receiving heat. So the entropy of the surrounding should increase. Okay. So delta S surrounding should be increased. So it's a positive. So it should increase by 600 over the temperature. Okay. So this is 600 over 298. Should be positive 2.01. Okay. Okay. So this heat transfer process makes the entropy decrease for the water, but increase for the surrounding. Okay. So together, you just sum up these two entropy changes. That would be the total entropy generation during the process. okay, which is positive, as you can see. Right? This is the total entropy generation. Okay. Or you could choose an extended system like this. Okay, including the pistons in the device and the immediate surroundings. Okay, so applying the entropy balance equation. Okay, so this delta S system is this guy, right? Because this system is the pistons in the device. Okay, and we don't have S in, but we do have S out. This S out is because of the heat rejection. Okay, so S generation in this case is delta S system plus S out, okay, which is minus 1.61, and this S out is Q over T surrounding. Okay, so that would be 600 over 25 plus 273, which is this guy. So this is 0.4 plus positive 0.4. Okay. Okay. So once again, this this entropy generation is because of the final temperature difference. Okay. So this heat transfer can happen naturally. Okay, this process can happen naturally because you can see the temperature of this system is higher than the surroundings temperature. So there's a heat loss process like this. Okay. All right. Questions about this? About chapter 7. This is the last one. Okay. The remaining slides are just a few summaries I made for you, including the entropy change of pure substance, incompressible substance, and for ideal gas, we know we need to, we have a few very nice equations, and we need to tell if the specific heats are constant or variable, things like this, right? Isentropic efficiency, there's a logic for this, right? Means efficiency has to be smaller than 1. So you need to know the device you are looking at, the purpose of that device you are looking at, and decide if when this device works isentropically, then its work is, or some other energy is supposed to be the maximum or is supposed to be the minimum. So you can adjust the position of the isentropic one and actual one to make sure the efficiency is smaller than 1. Okay. And entropy balance, we just finished this. Okay. Okay. All right. So that's all for this semester.